Should I start at 10?
Yeah.
Okay.
I think so. Or maybe a couple of minutes more, because I think that is the boundary which people are targeting. And
Which
maybe
is the boundary? My concern is that if I start at 10:02 tomorrow, I'll start at 10:05, and then by the end of the week I'll be starting at noon. You know. Right. So 1 minute.
yeah.
Okay. All right. Let me begin. Before I start with the topic for today's lecture, let me make a correction. Yesterday, when I was looking at the Stuckelberg trick, I told you something that is not always true, but it's almost always true. What I said was that the theory, because it has a unitary field like this, will become strongly coupled at a particular energy, at scales above a certain particular energy. This is true provided, I'm sorry, it's true always except in one single case. And the single case is when you have a single gauge boson W, so this big N is 1, and where you don't add any other vector bosons. So L is equal to 1 as well. So you have one gauge boson, you have one, don't have any additional ones. You have some other fields, that's as many as you want, but you have only one W. So if you have one gauge boson, one vector boson that's going to become a gauge boson, the only group that has n equal to 1, has one generator, is U1. So now you have a U1 gauge theory. In that case, this unitary field is very simple. It's just a complex number. It's e to the I theta. That's how U looks. And if you look at if you calculate this, you evaluate this thing for that particular case, the trace is very simple because everything is a 1-by-1 matrix. So the trace is very simple. There's only one Tn, one generator. Using my conventions that the generators are anti-Hermitian, that generator is just the complex number I. That's it. And so you can evaluate this thing, and you will see it's a very simple expression in terms of the W, the original W, and the exponent of the field U that I call theta. So if you write U equal to e to the I theta, then this curly W will become a linear combination of the original W and this theta in the exponent. And you will see that the ensuing theory is very simple. It's very simple. And so, but that's the only case in which the result of the Stuckelberg trick is that straightforward, that simple. In any other case, that is, when big N is greater than 1, and when L or well, where big N is greater than 1 and all, okay, and all L is greater than 1 as well, then everything I said last time is correct. So there's one exception when there's only one gauge boson and the group that you choose, this G, is U1. Okay, that's the one exception. You have nothing better to do, that's actually a nice exercise to follow. Any questions about that? All right, then let me remind you briefly what I did last time. I was trying to find a unified way of doing hierarchy, of specifying hierarchies among the effective operators that will be useful for a variety of applications. And for that, I defined this index that has two expressions this way and that way, and depends on this parameter u, which is an arbitrary parameter. But in practice, I will choose three possibilities for u equal to 4, u equal to 2, and u equal to 1. Those are the three cases that I will look at in more detail. And the reason why those are useful, I think, is when u is equal to 4, then the hierarchy that you get is typical of cases where the underlying physics, the new physics, is weakly coupled. U equal to 1 is useful for a particular flavor of SUSY. It's a nonlinear realization of SUSY. I will talk about it in a few minutes, not in detail, but I'll just mention it in a few minutes. And lastly, this is much more important, when u is equal to 2, the hierarchy corresponds to the one used when considering the effective theory approach to low energy QCD. Okay, so that's what. So I'm going to go through these three cases one after the other next. But before I do that, I wonder if there's any questions about what we covered last time. Okay. Of course, you can always interrupt as I go on. Okay. So first case u equal to 4, that corresponds to the standard model effective theory. In this case, the index is just the dimension of the operator. This is I remind you, little d is the number of derivatives in the operator. Little b is the number of boson fields or scalar fields for the standard model in the operator. F is the number of fermion field in the operator. And as you know, this is the dimension then of the operator. So S is the dimension minus 4, as noted here. And therefore, the operator will have a factor of lambda to this quantity delta, the mass dimension minus 4, in front of it to make sure that this object together has units of mass to the fourth, and so it can be put into the Lagrangian. I omitted putting a coefficient in front of it, since this is just for illustration purposes. And so what I've been arguing is that operators with smaller delta are more important than operators with larger delta, just because the suppression factor is smaller in the first case than in the second. And as you see, since S is really delta minus 4, smaller delta corresponds to smaller s. And indeed, the leading operators have smaller s than the subleading ones. All right, the next case is this one that I mentioned will correspond to a flavor of supersymmetry. I think it's the next slide. Yeah, in the next slide, I give you the specific Lagrangian for this case. S is chosen to be such that u is equal to 1, and to assume that all operators have at least one derivative. In this case, the index is just d minus 1, the number of derivatives minus 1. What we will get is that lambda, the general form of the operator, for the case of supersymmetry that I'm looking at, there will be no bosons. So and you'll see this in a minute. So let's assume for a moment theory has no bosons. So you have some fermions, some derivatives, and some suppression factor, like this. And as we will see later on in the course, there will be an additional suppression factor produced by the naturality of the theory that takes this form. Again, the larger the index S, the larger the suppression factor, the less important the operator is. So let me give you the example. Here it is. The reference for this is the book of Wess and Baga, Supersymmetry and Supergravity. I forget the chapter number. But they have a chapter on nonlinear realizations of supersymmetry. I'm not going to prove that this is a supersymmetric theory here. It takes me too far afield. But this Lagrangian here, written like it is in fact supersymmetric. But this A is defined in this way. And just a little bit explaining of notation. Sigma A are the sigma matrices. But in this case, they go for little a goes from 0 to 4. The a equal to 0 is just a unit matrix. So sigma 0 is 1, and sigma 1 to 3 are the usual Pauli matrices. This way of writing the Lagrangian relies on the chiral representation of fermions. So with this is a 4x4 matrix. You can take its determinant. It depends in a very nonlinear and complicated way on the fermion fields, and it is supersymmetric. The operators are obtained by doing an expansion in the number of fermion fields, and you find that the coefficient is of this order, provided kappa is of this order. And so what this argument gives is that, this argument gives is that the hierarchy produced by this index S here corresponds precisely to the one that is obtained from this Lagrangian, just by naturally, provided kappa, which has units of 1 over mass, has this form. It's again, so it's not a bizarre situation. The last part, so let me, I don't want to go through this in great detail because it's not really, it's an interesting intellectual exercise, but has, as far as I know, no practical applications whatever. What I want to concentrate on the rest, most of this lecture is the strongly interacting theories. So strongly interacting theories are difficult because they're strongly interacting. But they're not totally unmanageable. There's things we can say about them, even though we cannot calculate often with the precision that we'd like, or the precision that we obtain in weakly coupled theories. The generic form of operators that we find in strongly coupled theories is this. I mean, there's no mystery. I've attached different scales to the scalars, the fermions, and the derivatives to give as much freedom as possible. As we will see in a minute, these scales are not independent from one another. They're interrelated. I will define then a strongly interacting theory as one where loop corrections are of the same order, no matter how high the number of loops are involved. Now, I will not be evaluating all loops because it's very involved. So I will just be estimating in the following what the contributions are from various loop graphs, and then impose this condition, and see what I get. That's the thing. So I will choose an operator OA. So OA, it has a number of boson fermions and derivatives, and I will look at radiative corrections to it and require that radiative corrections will all be of the same order. In particular, they will give the same order effects as the tree-level effect, which is just the operator OA. In doing this, I will take the integration momenta to go from 0 to lambda that correspond to the cutoff scale of the derivative. I will assume that each loop gives a loop factor of 16 pi squared that comes from doing the loop integration. And aside from that, there's not much more to do than kind of estimate what any particular loop will give. All right? So, if you have a loop that has a bunch of, okay, I just realized I changed the notations a little bit. So, think of any loop graph. It has in it a number of vertices that correspond to effective operators. In particular, the vertex has a number of derivatives in it. So because of that, then the number of derivatives will show up as powers of momenta inside the loop integration. Each power of momenta I would simply replace by the worst possible scenario, that is lambda. So if I have a vertex that has dA derivatives, it will produce dA powers of momenta, and it will give a factor of lambda to the dA. So that explains this guy. Each loop integration gives, has a factor of d to the fourth. So I get a 4L factor in the exponent. Each propagator of the, each boson propagator has a power of 1 over p squared that corresponds to 1 over lambda squared. And so I get 2 inverse powers of lambda. And so we have this. And finally, the fermion, any fermion propagator will go as 1 over p and gives me 1 over lambda, and here it is. One thing. Sorry, something got in my eyes. I'm just trying to get it out. Okay. Okay, and so the power of momenta that we get is this kind of thing. Now you might ask, what is this power to minus d? That comes because I'm assuming that the graph gives a correction to the operator at hand, L, that has d external derivatives. And so that corresponds to d powers of the little d powers of the external momenta. And so that subtracts from the total, since I have, that subtracts from the total powers of lambda, because in the whole dimensional analysis of the graph, d powers, little d powers, must be accounted for by external momenta. And so they will not show up as powers of lambda, but as powers of the external momenta. And here I'm just calculating the power of lambda that I get. Then there are topological relations that that relate the number of internal boson vertices to the external ones and the number of internal boson lines, and similarly for fermions. And then you find that corrections that you can evaluate, basically it's this factor here at the top, are all of the same order if and only if this is true. So basically what I've done is I've considered a graph that gives a correction to this operator O. Oops, sorry. To this operator O. The graph is composed of vertices. The vertices are also produced by operators of this type that are called O sub A, with B sub A, F sub A, and D sub, little d sub A, and a factor of lambda in front. And the rest is simply estimating the contribution from such a graph by replacing the momenta by factors, by lambda. Each momentum factor is replaced by lambda. And so you get this thing from the graph with this n, and you use these relationships, and you require that this correction that you get is the same as the tree level. That is, the coefficient of the operator that you get is also lambda, little lambda. And when you do that, then this will be true of course, this has to be true for any choice of vertices, any choices of dA and of BA and so on, okay, then that will be true only if this is the case. So as promised, for the condition that I use for defining strong interactions, namely this, it can be realized provided the scales involved are related in this fashion and the overall coefficient of the operator is 1 over 16 pi squared. Okay. You can, let me refine this a little bit. Yep. What's that?
If you want to take this crash in the eye or something.
Oh, can I do that?
Yeah.
Okay, then I'll be right back. It's just something on my eye. I need to just put, let me turn off this. So I get a recess for 2 minutes.
Watch Virat Kohli in action. Excellent use of the feet. Sheer brilliance from Virat Kohli. Catches the ball, and he's gone over the top, using the bottom end to good effect. Virat Kohli is on a roll. This is big. This is massive. Brings up the
কোনো
200.
খেলা চলছে? হ্যাঁ, বিরাট কোহলি খেলছে আজকে? In যে প্রফেসর Prof
Sorry. Thank you, Shubha. Let me harp more on this calculation. In doing this this expression, I've taken these coefficients to be the same for all the operators, these little lambdas, and that's what you get in this case. Let me go back and look a little bit more at the possible corrections to the coefficient. And this now, I'm sorry, I changed the notation. This is what replaced the V is for vertex, so that replaces the index A that I've been using here. I am sorry, I just changed the notation. And so if you have a correction to this from an L-loop graph, you have a product of vertices multiplied by the loop suppression coefficient, and the condition for strong interaction is that the corrections will be of the same order as the tree level graph.
Yeah, that was the precise question. That till you reach to this point, this method is generic, right? Till you reach to this condition that lambda BF is of the order of delta lambda BF, the methodology that you have used.
It's completely. It's generic. But okay, so yeah, absolutely generic. But notice the twiddle. I didn't put equal. So that means it's just of the same order as that kind of thing. It's not intended to be a precise calculation. So the lambdas are of order 1 over 16 pi squared. kind of thing. So the correction to lambda will be of the same order because each one gets a 1 over 16 pi squared difference. Okay. So let's see if we can use this to evaluate to evaluate to evaluate the dependence of lambda on the number of boson and fermion fields. That's what I'm looking at now. To do that, imagine that you have a graph. I'm sorry, I keep changing this. Have a graph that has some external lines that correspond to a particular operator. And imagine that you replace inside this graph one operator by one that has two more boson lines, fields in it. Then this new guy will provide another correction to the same operators, same guys, kind of thing, where now I've taken these two boson lines and connected one to each other. Just made a tadpole graph of it, addition to it. So this is yet another correction to the operator, but it will be useful for the reason you will see in a minute. You see this this graph here now has two more boson lines inside. Has two more. So instead of being BV here, this guy has BV plus 2 because it has two more bosons. So what I'm telling you is that you have this guy here corresponds to this lambda because now I have two more guys. Times 1 over 16 pi squared is of the same order as this lambda because the only change that I've made is I replaced one vertex by one vertex with two more boson lines. Okay, so I replaced one another, and I made a very simple, of the many possible, one very simple and useful correction where these two additional boson lines are connected to one another. They're just a type. Because I'm assuming it's strong interacting, the original graph and this new graph will give the same corrections. And that can be true only if the vertex that I had before, from here, compared to the vertex that I have here, provided I include the additional suppression factor from the loop, are of the same order. I put equal, but in reality I mean of the same order. And if this is true, if this is to hold, for any, then the only way of, for this to hold, the only way this this can be realized is if the dependence of the number of boson fields is this. I can do exactly the same thing with fermions. I would not go through the exercise, but you will get this thing. So if you combine everything, you get a very precise estimate for the boson and fermion dependence, the number of boson and fermion dependence of the coefficient of lambda, which is precisely this. This is known as the naive dimensional analysis estimate of the strong coupling coefficient. For a simple case, simple cases it can be derived, in a case-by-case basis. I decided to do this in the generic case just to show that one can make use of the condition that the theory is strongly interacting as I defined it to extract some information. So now we have an expression of the coefficients dependence on B and F. Now let's put everything together. I have the estimates of these scales that I have here. I have estimates of lambda that depends on B and F. I have an overall 1 over 16 pi squared from an overall 1 over 16 pi squared. And I put everything together, and you get this expression for the operator, its coefficient in front. So again, it's not surprising that you get delta. I remind you, delta is the dimension of this thing minus 4. So whatever scale goes in front, it has to have the factor of delta, because only then you will get an object that has dimension of mass to the 4. What is more important here, or more useful, or less direct, is what lambda shows up here, and what, if anything, other factor comes up here in front of it. And from the previous argument, I know I've rushed through this, but I cannot go in full, I cannot do the calculation, just not enough time. I cannot do calculation in front of you. I'm just trying to describe more or less what I did. You get two things. First, you get one scale that I call lambda phi, a factor of 4 pi to the s, where s is this. Notice that this index s does not depend on the number of boson fields at all. It's independent number of boson fields. So the same coefficient would occur. The same factor, 4 pi to the s, occurs when b is 1 as when b is 10 to the 5. Doesn't matter. It's the same factor. There is a suppression factors of 1 over 4 pi to some power. And the power is determined by the index when u is equal to 2. So this really corresponds, and that's why the index again kind of unifies for different values of this parameter u various situations. For u is equal to 2, it describes the operators that occur in low energy QCD. I'll make further contact with low energy QCD in a minute. And it gives the suppression factor in front of it. The larger S is, the smaller the effect of the operator, and hence you get a hierarchy. So, the simplest example that I could think of is what are called chiral theories, or chiral QCD, or low energy QCD. And I am going to assume there are no fermions. So in this particular simplified version, there are no baryons. The baryons are not there. But there are pions, or more generally, they're mesons. The symmetry of that theory is SU2 cross SU2 chiral symmetry. This is a global symmetry. This is not the standard model SU2 exactly. It's related in some part of this symmetry is related to it. But this is a left-right symmetry obeyed by the theory. It's a global symmetry, not the SU2 gauge theory of the standard model. The standard model, in the limit where the quark masses are 0, or the corresponding Yukawas are 0, does satisfy this SU2 cross SU2 chiral symmetry. But I'm not going to try to go through that. I'm just going to argue that this is what is observed experimentally. And the simplest way of describing such a situation is using a unitary field again. In this unitary field, the meson fields, the physical meson fields occur in the exponent, but the Lagrangian that has the invariance takes this form to lowest order, and then it has higher order terms. The point is the following. Each term here, 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 and so on has derivatives, but has various numbers of the field U. Each field U has an infinite number of meson fields. Because when you expand this, you have 1 plus pi squared, pi cubed, plus, and so on, all the way to an arbitrary number. So this and this and this individually have terms that involve 2 pion fields, 3 pion fields, 4, 5, an infinite number of pion fields. So a hierarchy between operators, if it's to be useful at all, should not depend on the number of pion fields. And that corresponds to this situation, in that respect at least, because the hierarchy specified by this index S does not depend on the number of boson fields. And that is why, actually, not why, but that's one point of contact between them. The lowest possible non-trivial term that you can write down that involves this unitary field that satisfies the symmetry is this guy. Here. The higher order terms, well, they look like this. These are not the only ones. There's more. There's several more. Okay. And what I've been arguing here is that the operators O come from all these guys here. Notice that this scale here, Fp, appears here as well. Yeah, let me interrupt myself. Note that this F pi, which has units of mass, appears in front of this here as well, exactly as it is. The reason for that is to have a standard normalization for the kinetic term of the pions, so that the Lagrangian starts with d mu pi, with coefficient 1/2. That's why you have the same guys here. Okay, so think, but you can do the corresponding expansion of this thing. There are no fermions in my theory, so the index is simply the number of derivatives minus 2. So the coefficient you expect to be at most of this order from the previous argument. This is what this gives. And this is what this gives, provided F pi is identified with lambda phi and the coefficients C's are of this order. So for the case here, where we have 2 derivatives, the coefficient here is of order 1, and we only get lambda phi squared. For the next order term, the coefficients correspond to terms with 4 derivatives. So this will go like 1 over 4 pi squared, and so on. And so on. Now, what this does not tell you is how to get all these guys. That is hard. You have to work very hard, make sure that you get all the terms, and make sure that it satisfies the right left-right symmetry. But once you have that, then this argument tells you what order you can expect for these coefficients. Now, the beauty of this whole long argument is that low energy meson physics has been studied for many years, now 60 plus years. So there's an enormous amount of data. There's so much data that we can probe this term and find out the coefficient in front. And we can probe all these terms, the ones that have 4 derivatives. Not yet the ones that have 6 derivatives, but the ones that have 4 derivatives. And the numerical value of these coefficients has been obtained in every single, not for, there's more than 2, as I mentioned, there's more than 2. There's like 4 or 5, something like that. All those numbers have been obtained. And in all cases, they are of order 1 over 16 pi squared. There's no surprises, no mystery, no nothing. It just works, it justifies the previous argument, at least in this instance, providing an estimate for the coefficients. Okay, so this actually works for this. Now, before I leave this and ask for questions, let me just forewarn you, inevitably, one has to repeat Greek letters. And so pions are usually represented by fields that pi, labeled by pi with an index a. And the number pi is also represented by the Greek letter pi. This pi is not this pi. Okay? This is 3.14159, blah, blah, blah. This is a pion field. And I apologize for any confusion this might produce, but it's a fact of life that sooner or later you will find a confusing notation. This f sub pi refers to the scale associated with the pion fields, not that it's not associated with the pi number kind of thing. So, using naive dimensional analysis arguments, which is based on the statement that a strongly interacting theory will have will be characterized by having loop corrections be of the same order as tree-level effects, kind of thing. With that, you can get estimate for the coefficients of the operators that describe any type of interactions in such a theory. And what is interesting is that corresponds to the index, that can be, again, corresponds to the index that I've introduced as I said a priori, defining a hierarchy for a particular value of this parameter u. And it thinks it unifies the thing. But so that's kind of an interesting thing and maybe justifies the use of the index. But the really important thing in all this thing is the following. You can use the effective theory to construct operators that, or in this case perhaps more physical operators that describe the interactions among mesons or among physical particles. And the result is accurate. In the sense, it describes exactly what you see in terms of but a few coefficients. Even though the coefficients cannot be predicted by the theory, they can be estimated. So you have a formalism that tells you what the interactions are and tells you how strong they can possibly be. And in fact, in the cases that we have been able to test it, it works. So this is a proof of usefulness, a practical proof of usefulness of the theory. And so it gives us confidence that the whole approach of the effective Lagrangian that I've been talking to you about is in fact useful in describing nature. It actually is useful. It's not just an intellectual exercise, but it gives you good results that you can actually use. So if you had hoped to have a coefficient that went not like 1 over 16 pi squared here, but you say, for example, what else can it be? It has no units, so it has to be of order 1. You know? People make such arguments. And the answer to that is no, it can be another number, like 1 over 16 pi squared. You know, why not? So just making this hand-wavy statements as to, well, it cannot be anything else because, you know, it has no units, so it has to be of order 1, actually make no sense. Those have to be justified by an argument. Now, let me just make one point, additional point about this thing. If you decide to include baryons, which is perfectly possible, you get an estimate for this coefficient that now depends on the baryon number. And it doesn't look exactly like this. It depends also on the number of fermions in the operator. And the coefficients for some of the fermion operators are much larger. In fact, they are of order 1. There's nothing wrong with that. But the reason that you can trust that is that you made an argument, a coherent, consistent argument that led you to say, well, for that case, these coefficients are of order 1. Okay? You cannot just hand wave yourself into doing that. I keep on saying these things because in my lifetime, there was a strong trend to justify the construction of a collider, the lab collider, arguing that it would probe physics beyond the standard model immediately, that you would turn the collider on and you would see 50%, 100% deviations from the standard model. That was totally wrong, totally wrong. It was based on assuming, for no reason at all, that the coefficients of the effective operators would be enormously large, factor of 10, 100, sometimes even 1,000 larger than what they could possibly be. And so, effective theory approach is very nice. It works very well. But if you misuse it, you will get crazy results. And the only person to blame will be you, not the theory. Okay? So it's good. Questions? Yes?
So you have taken the lambda, the radiative correction lambda of the order of delta lambda. So like, is it an assumption or requirement?
Yeah, the idea is it's just the same thing as strong theory. You mean this? This?
Yeah.
Yes. This is the same thing as saying this is the requirement of strongly coupled. That the one loop correction will be just as large as the three level correction. And the two loop will be as large as the two one loop correction. It's just that statement. Now, the only thing to remember is the fact that you have sums of terms of the same order of magnitude, it doesn't mean that you will get infinity. Okay, you can, it sounds funny, but 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 doesn't necessarily give you infinity. It could give you something finite because it's not really 1, and because the signs are not necessarily all positive, and because there might be. So you have a general statement about this. I'm just saying something about each radiative correction compared to another. I'm not saying anything about the total sum. So I'm not telling you what the result is of doing an n loop, an infinite loop calculation correction to any particular process. I'm just saying that that my definition of strong interaction is that one radiative correction is as large in order of magnitude as any other. Other questions? Yes.
So, when you talk about the particular example of chiral symmetry,
Yes.
I mean that's being a global symmetry. I mean, what happens if you introduce an effective operator which doesn't respect the symmetry?
Yes.
That
You,
is also
you can do that. You can do. So the question is, what happens if you decide to purposefully break the symmetry? Okay. So breaking a local symmetry by hand is perfectly acceptable. You break a local symmetry by hand, and you accept the consequences. With this, you just, in fact, you must, as you probably know. The reason why you must break, oh no,
Which battery actually I have not answered.
my battery is low, and I don't have a charger. Ta-da! I hope you like the course. Thank you. Thank you very much. Okay. So this symmetry follows, as I mentioned, from the standard model. If you assume the quark masses are 0. If the quark masses are not 0, that is, the corresponding Yukawas are not 0, then this symmetry is broken. In fact, it's broken precisely by the quark masses. You say, but you don't have to go and say, oh my God, the end of the world, this is no longer applicable. That's okay. It's okay. You can add to this term. Now you have a different symmetry. So if all the quark masses are the same, instead of having SU2 cross SU2, now you have just SU2. And you can write down then, in that case, terms that have now this reduced symmetry. You keep this because If it satisfies a larger symmetry, it satisfies the reduced symmetry, but you can add more terms that include the reduced symmetry. And those are useful, in fact necessary, as I mentioned, because quarks have non-zero mass. And so you add terms here that describe the quark masses. As it is here, represented here, the quarks that you get, are quark masses because the pions have non-zero mass. As it is here, the pions are massless. There's no mass term for the pions, those whole bunch of terms. But pions do have a mass, and you can add it by including terms that violate this SU2 cross SU2 symmetry. That doesn't violate the recipe of using the effective theory. You have a different symmetry, you can add different operators. Okay. Again, remember part of your process in constructing an effective theory is finding what the low energy particles or the particles of interest are. In this case are the mesons, good. And then you're finding the symmetry of it. And then at the beginning, for simplicity, I've assumed that the symmetry is SU2 cross SU2, which is true if you ignore meson masses. And then you get this. If you have a more realistic situation, as one must do, then you must include meson masses. The symmetry is reduced, and the effective Lagrangian is correspondingly enlarged or altered. In this particular case, the meson masses, the pion masses, are sufficiently low that you can consider them as perturbations. If you kaon masses, they're a little bit too large. Pion masses are 100 MeV, kaon masses are the other 500 MeV. Other heavier mesons, you're out of luck. I mean, these are not a perturbation. This is not a way of doing that. They're just too heavy particles to take this approach. Okay, it's a different way. Other questions? All right. So let me move on to the next topic. All right. And this is what constitutes a lot of the spaghetti and meatballs, or the Dow and rice part of the approach to effective field theories currently. This is what you do if you're working on this thing just about every day. And so I'll go through this a little bit slow. I'll try to give a little bit more detail than in the previous slides because it's just so useful in the current environment. Okay. This situation corresponds to the case where the underlying theory is weakly coupled. The hierarchy, the intrinsic basic hierarchy of the operators, it's their dimension. And so dimension 5 is more important than dimension 6, which is more important than dimension 7. And people have calculated dimension 5, in fact, I'll almost do it on the board for you. People have gotten all dimension 6, 7 also. I hear some brave souls have gotten dimension 8 operators and even dimension 9 operators. I will discuss that. In fact, there's a program that you can use that will give you all the dimensions if you, with sufficient computing power and patience. But I will talk about the need for doing such things as we go along. So, with that, I'm going to look at constructing the effective Lagrangian for the standard model. What I mean by this is I'm going to assume that the standard model is the low energy light theory. And I'm going to construct all this series of operators that embody all the virtual effects of any kind of new weakly coupled decoupling physics, new physics, parameterized by a bunch of coefficients of these operators. Blah, first thing. The second, as I tried to emphasize in previous lectures, the O will be gauge invariant. Gauge here, invariant, refers to the standard model gauge, SU3 cross SU2 cross U1. As I said, the hierarchy is set by the canonical dimension. And as I will justify later, there will be one additional thing that's new in this thing, is the following. If you have two operators, O1 and O, that are proportional on shell, what that means is that if you impose the equations of motion, O1 and O give exactly the same effect, except for a proportionality constant, you can drop O1. I will justify that later. This is called the argument that tells you that you can do this, exclude this type of operators. It's called the equivalence theorem, and I'll cover it, as I said, in a little bit. This is useful because when you construct operators of higher and higher dimension, you get more and more and more of them, very many more. I mean, the number grows very, very quickly. And so if you can at least get rid of some of them, not by fiat, but because they are redundant, then at least reduces the number of operators, reduces the number of measurements you have to do to probe the new physics using this approach, and so it simplifies life. So that's why this is useful. Now, the standard model, as I will define it, is the standard model in its simplest form. So the neutrinos have no mass. There's one doublet, and one scalar doublet, and that's it. And, well, and then all the quarks and so on. But you can make it a little bit more complicated. You can imagine an enlarged scalar sector, which is not completely excluded yet. You can imagine adding right-handed neutrinos, because the neutrinos have a mass. And one way of just giving them mass is saying, I'm going to put a right-handed neutrino field and give them very tiny Yukawas. And that's it. Right? You can do that. And then your low-energy theory is modified because now you have more fields. You know, remember, part of the recipe is choosing what your low-energy fields are. You have more fields. You have different, actually, you have an additional set of operators when you add more scalars. You have an additional set of operators when you add right-handed neutrinos. Okay? So that's something one can do. Before I plunge in, there's a little bit of housekeeping that I'd like to do to make sure we understand one another. And that is basically notation. So as I mentioned, the gauge group will be SU3 cross U2 cross U1. The gauge fields that I will use for those are G, capital G for SU3, capital W for SU2, and B for U1. So these W's, unfortunately, these W's I will also use for the physical W plus W minus field, but I'm sure that they will cause no confusion. If the W has an index capital I, it refers to the SU2 gauge field. Okay? The generators for the GA I call TA, for the SU2 I call tau I. Okay? These are the Pauli matrices. These are the Gelman matrices. The indices. SU2 gauge group labels are capital Latin from the beginning of the alphabet. SU2 gauge labels are Latin from the middle of the alphabet. And I will also have opportunity to use family indices. They're lowercase, these are uppercase. These are lowercase Latin from 3/4 of the alphabet down. Also, we have matter fields. The left-handed lepton isodoublet I call L, and these are its representations. The right-handed charged lepton I called E. Now, this is not the electron field. It's just a generic for all three right-handed charged leptons. So the E1 will represent the electron. E sub 2 will, E sub with a family index, so it really has family index, P. So E sub P. E sub P equal to 1 is the electron. E sub P equal to 2 is the muon. E sub P equal to 3 is the tau. And all of them right-handed. Similarly, for the left-handed quark, you have Q, the up-type quark, U, D, and the scalar doublet phi, the representation. So, and again, U doesn't refer to the first generation. It will refer generically to all up-type right-handed quarks in all three generations, and they will come with a family index. All right. So, what I want to do very, very first, oh, it's 11, is what I want to do very, very first is ask if you have any questions about the notation, because I have to stop now. No, okay. So what I will do next time, this afternoon, is explicitly construct the dimension 5 operators in the standard model. I will just go step by step, telling you how it goes. And I hope you'll enjoy that, because I'm not going to do that for dimension 6 or 7. It's much more involved. But I will do that as carefully as I can for dimension 5. But that will be in the afternoon. And my apologies for stepping. But I'm stopping at 11:01. You told me to start at 10:01. So thank you.
Okay, so the key should be outside. And we are also planning to have one informal session with all the participants after the lecture that we have in the afternoon. So that will be over by 12. So then we were thinking that there are many people who have come from different parts, and it will be good to know each other. So we will have an informal introduction session by everybody, and you can come and introduce yourself, tell what you are doing. So that I think will be done before we break for lunch. See you after. Am I audible? Okay, so it's time perhaps. Shall we start? All right. So in this lecture, what I'm going to do, I'm going to introduce a little bit of neutrino physics, and I'm going to talk briefly about where effective field theory can enter into the descriptions of neutrino physics. Once again, I mean, we have some complementarity with what Jose is saying, and there is some overlap also that I will explain as I go along, and we will see that we will get some interesting phenomenological output perhaps. So once again, let us, it's always good to remind ourselves that we are, the base of our understanding is mostly the standard model, and which we elaborated in the last lecture, and it's a SU3C cross SU2L cross U1Y gauge theory, and we also have talked about that just the gauge theory itself doesn't accommodate any masses to the standard model particles. So for that, what we require is a mechanism called spontaneous symmetry breaking, and the spontaneous symmetry breaking will actually break this gauge group into a SU3C cross U1 electromagnetic symmetry, and the broken generators associated with this one will actually correspond to massive degrees of freedom, and that's what happens, that the W's and the Z, W and the Z actually becomes massive, and the photon and the gluon, which are the gauge bosons corresponding to these gauge groups, they remain massless, and that is dictated by the observation, because we know that the photons are massless and so are the gluons. And this is the content of the standard model once more. And where does the neutrino stand? The neutrinos are here, and the neutrinos are actually assumed massless in the standard model, and only the left-handed neutrinos are there, which forms a doublet, and this is something that we actually talked about in the last lecture. So this is the way that it is organized, that neutrino and electron forms a SU2 doublet, and in general it is denoted by this small l, and the right-handed electrons are there, which sits as a singlet, and which is a hypercharge. You remember that relation that we derived, that Q is equal to T3 plus Y, and that dictates the hypercharge assignments of this. So for example, here the hypercharge has to be y equal to minus half, so that the Q, the charge associated with the electron is minus 1, the Q associated with the neutrino is 0, and for the hypercharge of this ER singlet, that is actually equal to minus 1, so that the Q is equal to minus 1, because the isospin is 0 for the singlet. Okay? And let us remind about the Dirac mass term for the fermions, and it's usually written in terms of m psi by psi. You remember, you have seen the pre-Dirac Lagrangian, which has the mass term of this sort, and once you break it in terms of this chiral representations, and then it can be like m psi l bar psi r plus psi r bar psi l, because the other combination like psi l bar psi l and psi r by psi r, that identically actually goes to 0. Now, in order to have some particle massless, as we assume for the neutrinos in the standard model, one possibility is to say that the right-handed fields don't exist. If you do that, then it automatically tells that you cannot write a mass term associated with that person, and so that is the case for neutrinos, that for massless neutrinos as assumed within the standard model, there are no right-handed neutrinos. Okay? And there is also one point that you see that there are 3 families of neutrinos, and one each corresponding to the charge flavors, like for one electron there is an electron neutrino, one muon there is a muon neutrino, for one tau there is a tau neutrino.
Now, the question is why do we assume massless neutrinos? Because the experiments essentially suggest that. So, for that let us recall the first evidence of neutrinos that we actually gathered, and this is something that we talked about yesterday also. It was actually the nuclear beta decay. So, for example, you have a nuclei AZN which is actually decaying to AZ plus minus 1, N minus plus 1 with electrons or positrons depending on the Z and N numbers. Now, this was observed for, say for example, this particular case. Now, this is the only part which we actually could observe, and this produced this kind of beta decay spectrum in terms of number of electrons and the energies. And what was funny about this observation is that if it is a two body decay, then this continuous spectrum of the electrons could not be described very well, because you know the conservation of energy and momentum would basically require the electrons to be coming out with a very specific energy like Me plus 18.6 kilo electron volt for this particular reaction. And similarly, the conservation of angular momentum also tells us that you know it is not something which is well obeyed, because this parent particle must have a spin half, whereas because these final state particles are all spin half, requires the initial state particle to be either spin 0 or spin 1. So, both conservation of energy momentum and angular momentum were sort of being questioned if the decay is actually of this way. And there comes the desperate attempt from Pauli, and who says that okay, all right, this looks that there is something funny happening here, and he proposed that there must be one guy which we could not detect in the nuclear beta decay, but which is actually present. And there are immediately these properties which could be assigned to this invisible particle which came out of this decay process. That is the first thing, that because no detector could find it out, so therefore, it should not have any electromagnetic charges. If you assign spin half to this particle, then you can conserve the angular momentum, and should be at least massless to fit the end point of the beta decay spectrum. Actually, there is a little bit of more detail if you go back to your master level nuclear physics course, and the rate of the spectrum divided by the energy and momentum multiplied for the electron. This is if this is plotted in terms of the electron energy, this should actually, I mean, this shows a straight line, and this straight line actually favors massless neutrinos. However, in each experiment what it does, that it actually sets a limit for the masses of the neutrinos, and that is what they did, and it should be something of the order of some electron volt. So, this was also the first measurement of the masses of the neutrinos via this beta decay process. So, basically this postulate allows you to explain all the discrepancies in the nuclear beta decay, and the presence of neutrinos were kind of postulated via this process. However, this was not the discovery of neutrinos. So, I may mention that the discovery of neutrinos actually came much late. Sorry, once again you know some issues with the slides. Actually, it came much later. So, the discovery of neutrinos occurred much later, but this was the evidence of neutrinos that we gathered for the first time. Now, there is also this point that we mentioned, that there are three families of neutrinos which are present, and in that for that I would like to bring your attention to the interaction vortices that we actually discussed in the last lecture. And what are the interactions that neutrinos will have if you assume the neutrinos form, the left handed neutrinos form a doublet and there is no right handed neutrino, then there are only two kinds of interactions that you can form. One is what is called the charge current interaction. The neutrinos actually talk to the corresponding charge leptons with interacting with the interactions via this charged gauge bosons W plus minus. And we can also have the interactions of the neutrinos with a neutral gauge boson which was termed as Z mu, and both these interactions show this kind of CV minus CA gamma 5, or rather 1 minus gamma 5 interaction. And this is something that we actually discussed in great details in the last lecture, which basically gives rise to this kind of Feynman graphs for the neutrinos, like neutrino is interacting with a Z boson and with the corresponding charge lepton via a charge gauge boson. And the interesting point is that there are 3 copies of each of these vertices, which Jose mentioned as family indices which are present, like there is nu e with Z, nu mu with Z, and nu tau with Z, and the same with corresponding charge leptons, nu e with electron, nu mu with muon, nu tau with tau. So, there are 3 copies of each of these interaction vertices. And what is then I mean what is said in consequences of having nu e interacting with nu e or electron is that we assume an accidental symmetry which is called the lepton number or lepton flavor, which is actually conserved in each of these vertices, and therefore, we are not mixing between nu e and muon, nu mu and electron, and so on and so forth. So, that's one of the points. Now, this is also an interesting question to ask, that what is the experimental proof of the fact that there are 3 flavors of neutrinos are only present in the universe. Okay? And this was actually there are several attempts, many experimental evidences of that, but I will actually talk about one of the interesting aspects of doing this exercise via the Z decays. Now, the point is, when the Z, Z can decay to fermions, Z can decay to neutrinos, Z can decay to quarks and all this other stuff, right. But because neutrinos do not have electromagnetic charges in it, the decay of Z to the neutrinos are invisible, and that is what is attributed to the what you call invisible decay branching of the Z boson. Now, because the Z decaying to neutrinos or invisible stuff cannot be observed directly in the experiment, they cannot be measured directly, right. So, what is the way that we can actually get to know something about this particular interaction? This is the recipe or the prescription. So, calculate the observable Z decay, which we can do experimentally, Z decaying to fermions, all the charged leptons, quarks, etc. We can also measure the total decay width from the line shape at the resonance. This is one interesting point. And therefore, if we have these 2 informations at hand, then we can subtract to get the invisible decay width, because the total decay width must be the observable one and the invisible one together. And this was one of these earlier efforts at lab. So, this is the what you call the E plus E minus 2 hadron, which shows the presence of this resonance peak here, and from here you can actually get this information about the total decay width associated with the Z boson, because the propagator has this factor like p square minus m square plus the decay width. So, from here you can measure the total decay width. You can calculate the observable decays, as well as you can observe the individual decay rates for these individual states, like Z going to E, Z going to mu, tau plus tau minus and hadrons. So, once you have that and the total decay width, you can actually have an indirect measurement of this Z going to invisible state, and which was calculated in this way. So, this is actually from the PDG, and it was this indirect measurement at the lab experiment that actually occurred. Now, once you have the total invisible decay width of the Z measure, I mean indirectly inferred from these 2 observations of calculating the Z total decay width as well as decay width to the visible particles, then what you can do is the following, that you can always calculate this decay width, right? Z going to nu e bar, this is something which can be calculated. Ah, my goodness, what happened? Okay, so once you can calculate this thing, then basically you can fit this decay width to the observation of the total indirect decay width that you infer from this experimental results, and that actually, and when you divide that, you see that there must be number of neutrino flavors roughly equal to 3, and that was actually an indirect measurement that there are 3 families of neutrinos which are present and which was inferred from this kind of nice experiment. And subsequently all 3 flavors of neutrinos were discovered via charge current interaction, because you can immediately understand when neutrino comes and interacts with somehow the Z boson and scatters off, the final state neutrinos are not visible. But when you take this into account, like neutrinos coming and hitting with your detector with which there is an exchange of this charge gauge boson, the final state of that scattering experiment can be a charged electron. So that's the charge current interaction.
His discovery was earlier than the discovery of mu1 and tau1.
Earlier than discovery of mu1 and tau1? No. It was much later. It was much later. So discovery of mu1 and tau1 I think was before this whole exercise, yeah. Otherwise we didn't know that there are 3 families of etc. And we.
But this was expected. But this was expected.
This was expected means because this is as I said that you calculate the observable decay widths for the Z, you can infer the total decay width of the Z from the experiment, and from that you can have the hunch of what will be the invisible decay width associated with Z. Now given that the vertex for this Z with neutrinos, you can calculate the decay width of the Z to one of these invisible final states, and then the invisible total decay width once divided with this calculation will infer what are the number of flavors of neutrinos that you expect. So this is one of the nicest exercise by which you got to know that there must be 3 families of neutrinos which the Z boson is decaying to.
So when you say this charge current interaction,
yes,
so you can distinguish the flavors of flavors.
Exactly.
But, so there is lepton flavor universality, right?
Right.
But you cannot distinguish like coupling W to nu E or nu mu. So like whatever the branching fraction we get is same for all flavors of decays, right?
Yes. That's
then how do we
case.
distinguish, like it is coming from the mu or it is?
No, this is from the charge current interaction. Like, do I have a piece of chalk somewhere? I mean, then we can scribble on the board. Yeah, so basically the point is the simple, the charge current interactions will do this, that you have the neutrinos and here some scattering with some hadronic matter. So therefore, what you can do, that you can detect this guy, right, electron. You can distinguish between electron, muon and tau, that you can do. And so therefore, from this interaction you can say that what kind of neutrino is actually hitting the detector. There are more caveats to that because neutrinos also oscillate, and that I will come in a moment. But this is the basic point, that the charge current interactions can distinguish between the different flavors of neutrino which are actually in the initial state. Because the final state is a charged lepton of a particular flavor that you can distinguish and observe, right? Yeah. So this is precisely the way that all these different flavors of neutrinos could be discovered. Because you don't know about this guy, but you know about this guy. And from your Lagrangian, you know that the interactions are, flavor symmetric or flavor conserving or lepton number conserving, whatever way that you want to put it. All right. So maybe once again, can we have these two lights off a little? Or here are they switches? Oh, great. Okay, so let's carry it on. So now the point is, so this is all good, but so far we didn't talk about the neutrino masses. The point is, neutrino flavor oscillation bears the testimony that the neutrinos are massive. Now, why this is so, that and how this was actually inferred is a very interesting story. There are observations related to solar neutrinos, atmospheric neutrinos and everything. I will just illustrate it in terms of atmospheric neutrinos. Okay. Now, what happens that because of the cosmic rays, there are lots of pions. Jose talked about pions, and we have the same notation of pi, and this is not the 4 pi. So these are the pions which actually decays to mu plus and nu mu. Pi minus will decay to mu minus and nu mu bar. The kaons, mu plus to nu mu, k minus will decay to mu minus and nu mu bar. But the muons are not stable, they decay, and they decay to electron. And this is also an interesting point, that all the heavy leptons decay to the lightest lepton. That is because that the lepton number symmetry only allows the lightest of its kind to be stable. And this is the idea that we will also use for the dark matter physics in a couple of days. Okay, so the point is, then there is this decay, that muon decays to electron with a electron neutrino bar plus muon neutrino. Mu plus will decay to E plus, nu E and nu mu bar. Now, once you have this is the full reaction. Okay, the pion decaying to muon neutrinos and muons, and then the muon further decaying to muon neutrinos and electron neutrinos. Supposedly, you say that you cannot detect or distinguish between the anti-electron neutrino and electron neutrino, and the same is for muon neutrino and anti-muon neutrino, then you can roughly see that the ratio of nu mu versus nu E is 2:1, right? Because you have, consider one of these decays, consider one of these chains, pi plus decaying to mu plus nu mu, and mu plus decaying to E plus nu E nu mu bar. So you have 2 muon type of neutrinos and 1 electron neutrino, and you can add this exercise for the other stuff also, for the pi minus and the kaons. So roughly we should expect that nu mu versus nu E should be 2:1. But what turns out that the number of muon neutrinos were much less, and that basically raises this question that what the hell is going on, and it sort of indicates that the neutrinos must have oscillated from one flavor to the other. And this is so the Nobel Prize to Kajita and MacDonald, and this is the observation. So the point is, this is upward going neutrinos, flight length of blah blah blah, horizontal going neutrinos, the flight length blah blah blah, downward going neutrinos. So this is the the angular distribution, if you wish. This is the number of observed muon neutrinos, and so what you expect was this kind of a curve. Okay, but what was observed was this kind of a thing. So these are the observed numbers, in this brownish data points, and that once fitted with this neutrino oscillation possibility or probability exactly fits the bill. So this was one of the cases by which you actually have inferred that the neutrinos do not remain. So, if a muon neutrino comes out of your reaction, it does not remain as muon neutrino, but it actually oscillates into some other flavor. But the clinching observation of neutrino oscillation later came from Super Kamiokande, because there are other detector effects, etc., which could be sort of there are important detector effects that one has to take into account into this night calculation and so on. And there are similar observations also came from solar neutrinos, which actually indicate that neutrinos oscillate.
Excuse me.
Now, if the
Can I ask you a question?
yeah.
So here, how the number of muon neutrinos are calculated, like observed? Because is it via the same charge current interaction? Like
I think so. This is what I believe, because I know the only way that you can detect the flavor of neutrinos via their charge current interactions only.
okay, so maybe there must be some muons which is in contact with the muon neutrinos and get something from that, like that.
I think that is the only way that you can detect the flavor of neutrinos, as far as I understand. Jose, is that correct, right? I mean, because there is no other way that you can talk about the flavor of the neutrinos, because you don't see the neutrinos, unfortunately. So the only vision for this invisible particle is this charge current interaction, and we are unfortunate the dark matter doesn't do that. So that's how we haven't been able to discover the dark matter yet. Yeah. Okay. So yeah. So now this is an interesting question, that why does these neutrinos oscillate? And the answer is that if the neutrinos are massive, then the flavor basis can be written in terms of the mass basis, and this is the standard way of doing it. This is exactly the same that we did in the standard model to identify your xenon in terms of what you call W1 and W2, right? Or sorry, not W1, W2, B and W3, B and W3. So you write them in terms of this combination, and then you can in general then say that I can extend it for the three flavors, and there is this unitary matrix which enters into here, and one can easily do this calculation that this matrix must contain 3 angles and 1 phase. This is a multiplication of 3 rotational matrices, which gives rise to this famous form of the unitary matrix, and this is the phase factor, and there are 3 angles essentially, which are all measurable via different experiments that I will not go into the details, but there are 3 angles. This C12 is cos theta of 12, S12 is sin theta of 12, similarly C13 is cos theta 13, and so on and so forth. Okay? So this what constitutes this unitary matrix, and now you can also associate that the flavor basis at time t, which will have this additional factor of e to the power minus I e I t, and then you can calculate this conversion probability of oscillation from one flavor to the other, which is simply this expression of expectation of nu beta nu alpha t mod squared, and this is this expression, and once you put this form back into this expression, then the final form comes out something like this. So this is the conversion probability from one flavor to the other, and interestingly what you see that it has this bunch of ingredients of this neutrino unitary PMNS matrix or whatever that you call, together with the fact that this has this mass square differences delta Mij square L by 2E, where E stands for the energy of the neutrinos, L stands for the length at which you are measuring this oscillation probability, and so on. So therefore, I mean, if you can somehow experimentally observe this oscillation probability, this, because this depends on the delta m square, you can actually do the reverse exercise precise because you know the L, you know the energy, and if you know this observable like P, then you can extract the delta M square. Delta M square means the mass difference between the different mass eigenstates of the neutrinos. And this is what was done. And well, of course, this is the oscillation probability in vacuum. Now, no, in practical cases, this is not really the case because there are matter effects and you have to include them. Devajyoti is an expert. I mean, I'm sure he's smiling over there. So, that you have to include, and then this probability gets modified. But whatever it is, eventually you can extract the delta M square. And this is what the present scenario is. The present scenario basically says that the atmospheric neutrino observation cannot decipher the hierarchy between nu2 and nu3. So, therefore, there are two possibilities which still are surviving. One which is called the normal hierarchy, normal because you have the nu1 to be the lightest, nu2 sit in the middle, nu3 is the highest one. And the other possibility is the inverted hierarchy where you can have nu3 at the bottom, nu1 sitting here and nu2 over here. Importantly, the solar neutrino observations fixes the hierarchy that nu2 is heavier than the nu1. So, therefore, this hierarchy is known. So, that is here also reflected. The one that we do not know is about the nu2 and nu3, and that is where these two possibilities actually arise. And here in the color is actually the amount of electron neutrino present in nu1, amount of nu mu which is present in nu1, amount of nu tau which is present in nu1, and the same goes for all these three mass eigenstates. And we haven't been able to resolve this mass hierarchy yet. So, here I would like to tell a little bit of story. So, when I was finishing PhD, I was going at different places for for job talks, etc. And one was at Jose's place, and there was a famous neutrino physicist, Professor Ernest Ma, who retired, I think, Jose, right? So, that time in India we were planning to build a detector, and that was called Indian Neutrino Observatory or INO. And there was a huge amount of excitement that the INO actually can resolve this debate of whether the nature favors inverted or the normal hierarchy. The unfortunate story is that experiment was never built. The reasons are political, but this is what happened.
But you got a job.
I got a job. I got a job because I didn't do neutrino physics. Okay, so then there are other limits, like there are direct limits from different experiments, like mu is of the order of 0.8 electron volt. There are cosmological observations which also gives you a limit on the sum of the neutrino flavor masses of the order of 0.12 electron volt and so on. And this is a huge table if you look into your PDG, which actually gives you all the inputs of your PMNS matrix, the different mixing angles, everything, I mean not everything, to a very precise order. Like for example, the delta Cp has not been yet measured to a very great precision, but like the theta 12, theta 13. Theta 13 was the latest discovery, I think, regarding the neutrino sector, which earlier was not there, and people used to write models like A4 which favors a 0 theta 13, which gives rise to what you call the tri-maximal mixing matrix. But this is the latest status of neutrino physics. Now, before we go ahead to say where exactly the effective field theory can take entry for the neutrino masses, I will briefly discuss the Dirac versus Majorana masses for the fermions. And the first thing that we do is to define what is called the charge conjugate for the Dirac spinors, and this is how exactly you define it. Psi c is equal to c psi bar t. Whenever you see psi c, okay, this means that this is c psi bar t, where c has a specific representation I gamma 2 gamma 0, and this is specific to Dirac-Pauli representation, I guess. And then you can apply that and you get an expression for psi c in terms of I gamma to psi star. Okay. Now, what it does, the charge conjugation basically takes you from electron to positron. It gives you the charge conjugate. So, pictorially you can say, okay, all right, so this is how it is, and once you do apply the charge conjugation, then the plus becomes minus and vice versa, keeping the spin orientations the same. So, now the point is that neutrinos are electromagnetic charge neutral. So, neutrinos being electromagnetic charge neutral can be its own antiparticle, and that is when it can be called a Majorana fermion or a Majorana particle. And this was, of course, I do not have to tell the name of this person, he is Majorana, and once again the slide goes. And so what is a, so then what you can say that this nu m, the spinor, can be written in terms of nu L and its charge conjugate. So, nu L plus nu L C. So, therefore, now if you want to write the mass term associated with nu m, so you can say that this is m m nu m bar nu m. Now, it is not very difficult to do that. Once you write nu m in terms of nu L plus nu L C, this term will actually come out to be nu L C bar nu L plus nu L bar nu L C. Unlike the Dirac mass term where we had this psi L bar psi r plus psi r bar psi L. Now, for the Majorana case, you have this kind of this thing. Now, why I am writing in terms of L? Because we know in the standard model there is only left-handed neutrinos. But you are absolutely free to do the same exercise assuming a right-handed neutrino and write a Majorana mass for you. Okay? So, you can write a Majorana mass term for those kind of particles, for example, neutrinos, and for dark matter if you wish, if they are fermions, to assign a Majorana mass term. However, there are two immediate consequences that we see, that first of all the lepton number symmetry is broken, because we argued that we have given a lepton number assigned for the nu L, and for the nu L C, therefore, I mean nu L C bar, the lepton number will be the same. So, it will violate the lepton number by 2 units, right. And the same, this term also does the same thing. And also you can say, okay, it is not only that, but also it is the U1 symmetry. When we talk about the left-handed neutrinos which are present in the standard model, when we write a term which is like nu L C bar nu L, that also breaks U1 symmetry, because the U1 symmetry number that are assigned for nu L is the same for nu L C. All right. Now, the Dirac mass term, if we want to write, requires the presence of a right-handed neutrino, and this is something that we have talked about. And we know that this kind of mass term that we talked about yesterday is also not allowed within the standard model. This requires an Yukawa interaction. Now, we can say, okay, first of all, what we concluded from the last slide, that neutrinos are massive. So, we have to somehow allow the neutrino masses. Whether we want to do it via this Majorana mass term assigned for the neutrinos, then we say, okay, all right, we can do that, but that will break the lepton number symmetry as well as U1y symmetry. We do not want to break it by hand at least. And then you say, okay, all right, let us do the same exercise that we did for other particles in the standard model to generate this kind of a Dirac mass term by assuming the presence of a right-handed neutrino, and we write an Yukawa interaction which we wrote yesterday, and that will be something like that. Oh, okay, it should better be written in terms of L bar, I guess, L bar H tilde nu r. I am sorry for this typo. But the point is, if you assign this kind of interaction term, because the neutrinos masses are of the order of electron volts, requires an Yukawa coupling which is as small as 10 to the power minus 12. So, that gives you a feeling, okay, all right, this is very, very tiny and we do not like it. Then the question is, what is the option of addressing the neutrino masses, because we have to do that, because nature has already showed via neutrino flavor oscillations that neutrinos better be massive. Now, how can we do do that. Before we do that, I mean, this has been shown by Jose, Joydeep, everybody, but I think it's good to repeat that what are the mass dimensions of the fields, and you know, the mass dimension of the mass and the momentum is 1 unit of mass, which I call E plus, and in H cross equal to C equal to 1 unit, the X has the dimension of inverse of energy. And this is simply because delta x delta p is of the order of H cross, which has which is unity here. The action which is in the 4-dimensional space time d4xl, so therefore this is dimensionless, so therefore the L has mass dimension 4. And so therefore, you know, now you look into the scalars, you know, the scalar sector is del mu phi, and you know that x mu has a mass dimension inverse, 1 inverse mass dimension. So therefore, and so there are 2 mass dimensions which are actually eaten up here, leaving only 2 mass dimensions for these 2 phi's, and therefore you can conclude that the mass dimension of the scalar field is 1. For the gauge bosons, I am sorry, it doesn't like gauge bosons. For the gauge bosons, the free Lagrangian is -1/4 f mu nu, and we all know this is the field strength tensor, and f mu nu is defined as del mu nu minus del mu mu. And once again, if you assign 2 mass dimensions associated with the derivative fields, the well, first of all, if this has to be mass dimension 4, this has to be mass squared, and then therefore a mu has to have a mass dimension 1. But for fermions, this is the free Dirac Lagrangian, and the interesting point is there is only one derivative term, and so therefore the mass dimension 4 has to be divided into one derivative and 2 fermion fields, and that tells you that it has to be mass dimension 3/2. So once we have this notion, now if Jose asks you that I want to construct the mass dimension 5 operators, then you know that how to construct them. So you have the fermion fields which has mass dimension 3/2. Scalars, there is one scalar in the standard model which is the Higgs, which has mass dimension 1. The derivatives which has mass dimension 1, and then you know what else, the gauge boson fields which also has mass dimension 1. And now you have to construct the gauge invariant, Lorentz invariant operators of any mass dimension that you want. Okay? All right. Now, what is the relation of this whole discussion to the neutrino masses that we have been talking about? And this is because of the fact that we can construct one effective operator in dimension 5 which looks like n bar nc, where n is defined as phi Dirac epsilon L, where epsilon is I tau 2, which is 0 1 minus 1 0 in the Dirac-Pauli representation. Okay? Now, the construction of this particular operator, Jose is going to elaborate soon, I mean in some hours, right? But this operator has a very interesting point, that if you give the vacuum expectation value to this phi field, what was the phi field? Phi field is this Higgs isodoublet that we introduced. Once you do that, you can see that this term looks like Cv square by 2 lambda nu L C bar nu L. And then you can say, all right, so this coefficient is nothing but mu, and this is nu L C bar nu L. Suddenly the volume drops, is it? No, it's okay. So therefore, what it does, this dimension 5 effective operator basically generates a Majorana mass term which violates once again the lepton number by 2 units. So we have arrived to that Majorana mass term that we introduced, right? But not directly. We didn't write it by hand, but what we did, that we wrote a dimension 5 effective operator, gave the Higgs a vacuum expectation value. So it's also sometimes similar to the spontaneous symmetry breaking mechanism. So the dimension 5 effective operator was gauge invariant respecting all the standard model symmetries, no violation of lepton number, no violation, no, not sorry, lepton number is still violated, but no violation of U1Y hypercharged symmetry directly, but gives rise to the neutrino mass involving nu L C bar nu L. So, this is a Majorana mass term generated for the nu L. Yeah. Okay. So, this is something that I have already stated, and this is Weinberg for you. I mean, he is known for many different things, and this is a screenshot of his paper, which actually talked about this operator. Now, the question is what kind of new physics, because Joydeep yesterday told you that whenever you find an operator, effective operator, this effective operator can also be generated from some specific new physics, right? Now, the question is what kind of new physics that can generate this kind of effective operator, and this is a schematic which says that there are three possibilities. The first one that we have in the picture, which actually has a right-handed neutrino in it, and what you can do that you can write an Yukawa coupling in a standard model gauge invariant way, connecting the right-handed neutrinos Higgs and the lepton doublet. So, this is a fermion isosinglet of 0 hypercharge, that is what is called the right-handed neutrino, and that once connected, and if you integrate this heavy field out, you can actually generate the dimension 5 effective operator. Now, the same exercise you can do assuming a scalar triplet of 0 hypercharge and a fermion isotriplet of 0 hypercharge. Okay? Now, these are the three possibilities of generating this dimension 5 effective operators, at the tree level. Now, why these are the three choices? This is simply coming from the group theory, because one can construct gauge invariant interaction terms involving the scalar isodoublet and this left-handed doublets involving either a fermion isosinglet, a scalar isotriplet, or a fermion isotriplet. So, this is the three things. But now, Jose is going to tell you more that you can do the same job at the loop level, and there are more possibilities, and which are perhaps more promising in a phenomenological way. Okay? Any questions up to this point? Okay, so let me proceed a little. Yeah. Yeah. So, the U1Y violation is once again, you remember that you have this nu E to form a doublet, right? I mean, the left-handed pieces forming a doublet, correct? And then the question is what is the hypercharge associated with it, and the point was that so this has the hypercharge y is equal to minus half, correct? And why that is so? Because I have said that I know the only one key formula, which is q equal to T3 plus y, and this has a plus half here, minus half here, gives you q equal to 0. For this guy, q is equal to T3 plus y, and this is actually, once again, this is a downward component for the doublet. So, this has T3 equal to minus half, this equal to minus half, equal to minus half. So, the point is, once you assign this, this has y equal to minus half. The point is that when you have m nu, so nu EL has a specific hypercharge, which is y equal to minus half. When you write the m nu term, that is essentially nu c bar nu c bar, this kind of a term, right, plus. The point is that if nu L has the hypercharge of minus half, mu L bar C, which is C nu L bar T, that will also have the same hypercharge. So, this is, if this is minus half, this is also minus half. So, this will have a net U1 Y charge of minus 1, and that basically says, okay, the term is not U1 Y invariant, right. So, that is basically the point.
No matter what dimension effective operator we write,
No, this is not true. So, the point is there are many operators that at the dimension 6 level that you can write, which will not violate the lepton number or lepton number or lepton flavor violation. There are lepton flavor or lepton number conserving operators, many operators that you can write at dimension 6 level. Unfortunately, the one that you can write at the dimension 5 level is a lepton number violating one. That is the only one that you can write in a gauge invariant way. Yeah. More questions? Okay. If not, let me proceed further. So, in a sense you can say that this is the pictorial representation, that you have a right-handed neutrino having a Majorana mass. When you integrate that one with LHN interaction will give rise to this standard model effective operator, which looks like the Weinberg operator. Okay. So, the integrating out the heavy right-handed neutrinos, one can get the dimension 5 effective Weinberg operator, and you can get the neutrino mass generated. That is very important when you give the Higgs the vacuum expectation values at the same time. Now, you can ask this question, that considering this dimension 5 effective operator, do you get any other experimental signals? I mean, you might be interested in asking this question, because we have been saying that whenever there are effective operators present, they can also show some signals via different observations. The question is whether this kind of operator does anything else for you. The answer is no. It only generates neutrino mass for you. If you are not happy with that, then we cannot help. But the dimension 5 effective operator that we talked about is very nice. It generates the neutrino masses, but there is no proof. At the effective operator level, you cannot say whether you have a new physics like a seesaw 1 or seesaw 2 or seesaw 3. There is no way that you can distinguish between these three. The only possibility and the hope is that if your energy scale reaches to that level where you can produce those new physics excitations and exploit their individual Yukawa interactions to produce them and decay and do blah 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 and other stuff and say whether they are there. From the low energy point of view, I mean, if your energy is not high enough to reach up to the scale of the seesaw masses, there is nothing else that you can do. So, they are very nice, they will generate the neutrino masses, but yeah.
Sir, so can we get some virtual effects, new physics effects at low energy scales?
Yeah, that's a very nice question. At least at the tree level, we don't know. At the virtual level, Jose, I don't know. The virtual effects of this, the Weinberg operator, does it produce some observable effects in, say, for example, collider?
At the loop level, we have a full model. So there's a neutrinoless double beta decay.
Yeah, neutrinoless double beta decay is a possibility. Yeah.
Phenomenology, the model.
Yeah.
Those are the main lepton number violation effects.
Yeah. The only possibility is to probe in neutrinoless double beta decay. I think that's a very important point. Yeah. Okay, so I will just give you a brief discussion on the right-handed neutrinos, because right-handed neutrinos are very nice and they generate type 1 seesaw, and you can write a standard model gauge invariant interaction involving the right-handed neutrinos. At the same time, you can generate a right-handed neutrino Majorana mass term without violating anything, because right-handed neutrinos do not even have the hypercharge. The hypercharge is 0. So, that will be not violating the U1y hypercharge, which you are worried about writing a direct U1y hypercharge violating new L term, a Majorana mass term for the. And this is the gauge invariant Yukawa interaction. This is the Majorana term, and what happens that in presence of the right-handed neutrinos, you can of course write a Dirac mass term also. So, the total neutrino mass matrix will look like this, involving nu, and so this is your standard model guy, this is the right-handed neutrino that you are introducing, and the mass matrix looks like this, and this is the Dirac mass term that you can generate out of this, the usual standard model mechanism via the Higgs expectation values. And then what happens that, so these are the Dirac mass terms for you, and upon diagonalization what you get that the lightest neutrino mass to be m squared divided by m, where this capital M is the heavy right-handed neutrino Majorana mass. So, evidently if you do not want to fine tune the Dirac mass term, which was the argument that we provided, the way that you can do it is to choose this M heavy to be very heavy, and if you want this light neutrino mass to be 0.1 electron volt, this capital M has to be of the order of 10 to the power 14 GeV, and this is precisely why this mechanism is called seesaw mechanism, because there is a heavy mass which is sitting downstairs to keep this light neutrino mass very light. Okay. How many right-handed neutrinos? Experts will tell you that at least you may have 2. I mean 3 is better, but 2 at least you require. 1 is not good enough. Now, right-handed neutrinos are like Bible of the cosmologists, because it generates what you call the matter-antimatter asymmetry via leptogenesis mechanism. So, you have this kind of Yukawa couplings together with the standard Yukawa and this Majorana mass term, and this right-handed decays to L and H at the tree level and via the loops to generate what you call a CP asymmetry parameter, and that enters into the Boltzmann equations. And if you have, so therefore you have the C and CP violation out of equilibrium, because you want to keep this decays out of equilibrium, because if it is in equilibrium then this asymmetry generated will be washed out. This is what is followed from what is called Sakharov condition. And once again, if you solve the Boltzmann equation, it looks something like that. This is for the right-handed neutrino decaying, this is the lepton asymmetry that saturates, and that's it. So, therefore, right-handed neutrinos are kind of a very important ingredient in constructions, and Jose, as he will talk more, that you can actually construct the effective operators assuming that we have right-handed neutrinos there, together with the standard model particles. And at the dimension 5 level, now you can have 2 additional operators like nu bar nu c, phi dagger phi, and you can also have a nu bar sigma mu nu nu c b mu nu kind of operators. And there are different possibilities of new physics. The way that we could talk about the models which can generate the Weinberg operator, you can have models which generate this kind of interactions. The one which is obvious is, for example, a scalar singlet with 0 hypercharge coupling to phi phi and nu nu, right. So, this once again follows from the group theory. Okay. And similarly, you can do the same for this guy. I am not going to elaborate on that part. Yeah, this is a quick check which you can do before you come to Jose's next lecture, that when we assign or construct the operators including the right-handed neutrinos, we often define this n, which is phi dagger epsilon L, where epsilon is I tau 2, and we define this capital E. This is not the electron, but this stands for phi dagger L. And if you expand these terms in unitary gauge, then you will see that n has this v by root 2 nu L, and E has v by root 2 E L, and so on and so forth. So, yeah, so I am not going to elaborate on these parts. I think my time is also coming to an end. And the point is, I mean, because you know the mass dimension, you know the quantum numbers associated with all the standard model particles as well as with the right-handed neutrinos. So, you can in principle construct the operators at dimension 5, dimension 6, dimension 7 level, depending on how much patient and enthusiastic you are. And so, there are these are the operators involving the right-handed neutrinos is mass dimension 6. These are classified into two categories. One category where there is no violation or baryon or lepton number, that simply involves nu bar nu kind of a term. And whenever, for example, you have a term like nu bar nu c, then you know that they will violate lepton number. And when you make it square, then they will be violating lepton number by 4 units. And similarly, you can look into these possibilities of operators. And this is the same exercise for constructing operators at dimension 7 level. There is this interesting possibility which we just briefly talked about neutrinoless double beta decay. I will hurry through this slide because I think Jose has also will discuss the possibility. The basic ingredient is the fact that there are some cases of even nuclei for which you see double beta decay, but double beta decay associated with neutrinos, that is not fun. I mean, because whenever there is an electron emission, there is a nu e bar emission to conserve the lepton number followed from the beta decay, right. So, it is simply beta decay, but it is not a single beta decay, but it is a double beta decay. But the question is, can we have neutrinoless double beta decay? Because if that is there, then that can be a test for the presence of lepton number violation to be very specific. So, for example, the case of right-handed, the case of not right-handed neutrinos, but say for example this operator, the Weinberg operator, which produces Majorana mass for the left-handed neutrinos, can produce this kind of a diagram, and this is actually one example of a neutrinoless double beta decay, where interestingly there is another observation that all the helicities of the electron that come out, because it is a Majorana mass associated with the left-handed neutrino, these helicities are always left-handed. This is an interesting point, and if you take other operators, higher dimensional operators, there are possibilities of generating neutrinoless double beta decay with different chiralities of the electron. That is a very interesting case. I will not elaborate on that part, but the fact is that it has not been observed yet, which predicts that the half life should be greater than something like 10 to the power 27 years. And there is an interesting connection to the neutrino physics that we talked about, that the neutrinoless double beta decay can distinguish, if observed, can distinguish between the normal and the inverted hierarchies. So, this is an interesting point. Yeah, so as I just mentioned that you can have a dimension 7 operator which can produce a, you see this is a lepton number violating operator, but it explicitly involves a right-handed electron. Once again you can check the gauge invariance of this term, and this will produce one left-handed lepton and one right-handed charged lepton. Similarly, this dimension 9 operator, which is constructed only with ER bar ERC, will give rise to 2 right-handed electrons, and at the same time will produce neutrinoless double beta decay. So, there is a huge prospect of probing lepton number violation at colliders, but not all operators can do that. So, I will just mention briefly the possibilities, like say for example, if you take this kind of operator, dp bar gamma mu ur, something like some LC bar I, there are many indices I, j, blah blah blah. This I is the complex I, this I is the family, this j is the family, and so on. So, this can generate an interaction which is like pp coming from this part dp bar gamma mu er, and this will generate this L bar LC bar d mu L, this will generate 2 leptons of same sign with a W, and this W can decay to 2 jets, giving rise to a signal which is like, and the same thing can happen from this kind of operators, but there the interaction vertex will not exactly be the same, but it will produce, if you expand this term, it will have a term like W plus square EL transpose C EL, I mean basically EL C bar EL. So, therefore, it will generate a term like ELWW, and that is what is happening here. So, you can have a initial state quarks via W producing a EEW. So, this will also, once again this W can decay to 2 hadrons and can produce a signal which is like same sign dilepton plus dijets at the LHC. So, there is a possibility that these operators, this kind of lepton number violating operators can be probed at the collider, and there have been some efforts in doing that. Okay. But unfortunately, no confirmed access from LHC yet. So, I will just skip this slide, and I think it is time. Yeah, this is the last slide. So, I think Jose, you are going to talk about the neutrino masses at the loop level a little, right? No? Okay. Okay, that is my job. Okay. So, the point is, see, for example, I mean, if you look into this kind of operators, you can actually generate Majorana neutrino masses at one loop level, and if it is generated at one loop level, there is an advantage. What is the advantage? That this brings the new physics scale down, because you know, there is an additional suppression factor of 1/16 pi square already sitting for you. So, therefore, it is easier to see the deviations which are coming from the presence of those kind of operators in experiments, because if you take the usual seesaw models and if you just try to probe them, yeah, I am overshooting, I will stop. If you take the usual seesaw models, the scale of the new physics has to be as heavy as 10 to the power 14 GeV, and it is very difficult. At least we do not know of many experiments that can reach to that heavy scale. But whenever you talk about these effective operators that can generate Majorana neutrino masses at one loop or more loop levels, the new physics scale lambda does not require to be that heavy. It can be of the order of even 10 to the power 4 GeVs. So, LHC with high luminosity can probe the effects of those operators. So, this is an interesting prospect where people are working upon. Okay. Okay, with that, thank you so much. Questions?
At the pre-level, basically what happens is that the Wudka couplings need to be fine-tuned the -2 layers. So, sir, if then the what comes to the rescue is the seesaw mechanism, that the mass suppression is there. So, what if you do seesaw mechanism and also that fine-tuning problem? And as you mentioned that with 1/λ suppression, we take some additional scalar fields and they transform under certain discrete symmetry groups, and there is a sort of means they collaboratively means they adjust the neutrino mass to the electron volt scale. So, is there any fundamental problem in there? Because
see, the point is, I mean, you can always say that ultimately when you are generating neutrino masses, they are very small. I mean, why they are small, that we cannot answer. Nature chooses to be that one. Now, in order to get that, if you just use the right-handed neutrino stitch to these Wudka couplings, I mean, with the standard model Higgs isodoublets, etc., then you require very small Wudka coupling. But on the other hand, when you involve the seesaw mechanism, there is a fine tuning, because there is a mass that has to sit downstairs, which has to be very, very heavy. So, either you have to deal with a very small Wudka coupling, or you have to deal with a new physics which is very heavy and almost decoupled and which you cannot probe. So, in a sense, you are translating the smallness of the Wudka in terms of the heaviness of the new physics that sort of can generate this kind of small neutrino masses. So, I do not know, I mean, whether you can call it a very natural, I mean, I do not have a very educated answer for.
There are 4 scalar fields supposing the term 1/λ, something
4
4 scalar fields.
scalar fields.
Suppose there are 4 fields that are 4 scalar, suppose.
LH you mean?
Yes, suppose.
Yeah.
Beyond standard model. So, their Wudka expectation values will.
No, but we are not constructing operators which has beyond the standard model ingredients right now. Our efforts are basically focusing on constructing the effective operators using the known physics, which are the standard model fields only. So, the Higgs that we are using is known. The question whether the Higgs is the Higgs that we have proposed in the last lecture is a question, and there the effective operator also comes into picture, which I will talk about in tomorrow's lecture. But the questions are basically we are constructing of all this set of operators, which are constituted of the standard model fields. Now, if you are for example, someone like Niloy who wants to generate leptogenesis at every day and every night, so he requires right-handed neutrinos. So he requires right-handed neutrinos, and he says that I cannot live without the right-handed neutrinos. So we are being a little more gracious enough to include the right-handed neutrinos into the known list of standard model particles and constructing the effective operators with them also. So this is what. Otherwise, the effective operators that we are seeing or we will be seeing mostly will involve the standard model fields and their symmetries.
Can you show in the graph that you showed in the Boltzmann equation?
Yeah. Hope I am not far away.
Yeah, so there are 3 lines. One is the equilibrium, actually 4. One is the equilibrium line, one is that the N1 is decaying,
Yes.
one is asymmetry, and the last one is?
So this is the asymmetry, and this is actually for the delta L, I guess, no? What is the difference between these two? So I think, there is this.
It is like for one is for initially I put the right-handed neutrino at equilibrium, and another is initially.
Okay. These are the same things. I mean, in one case you say, well,
One is a dynamical
one is
equilibrium
dynamical, and the other is assuming the right-handed neutrinos in the equilibrium.
Okay, and one you said that this there are prospects that we can check the new physics at colliders. So can we do that and not just proton-proton colliders like LHC, but muon colliders as well?
Yes, of course. I mean, that is something that we are, Ovik is proposing. That he is saying that you build a same-sign muon collider, and we can probe the lepton number violation. I mean, the usual mu plus mu minus collider will not have the possibility of probing lepton number violation. I mean, there are different kinds of new physics and a bunch of new physics prospects, but lepton number violation you cannot probe in E plus E minus or in mu plus mu minus collision. But you have to have a same sign leptons to be hitting, otherwise it's no fun. I mean, you cannot produce the same sign dilepton at the final state. Yeah. So proton colliders, however, can do that, because the proton can have, you take UD bar or something, whatever. Yeah, you can produce those, as I just showed via those graphs, that there is a possibility that you can produce EEWW at LHC, but not at the next generation E plus E minus or mu plus mu minus colliders. For that, you need to be a same sign lepton collider.
Sir, it's about the dimensionality of the operators, and we are setting the limits on these operators based on these experiments, like an upper limit. But my question is, this hypothesis that we are making are at a particular energy scale. Can we have more than one operator which generates this Majorana Mustem?
No, unfortunately, no. I mean, this is sad, but this is what Jose is going to show you in a moment, that using the standard model fields and respecting the standard model symmetries, there is one single operator that you can write which obeys, which is gauge invariant, and that is basically NC bar n, where n is defined like phi dagger epsilon f.
So the operator dimension will not change when I probe the experiment to different scales.
I didn't understand this question.
Because
maybe we can take up this question later. I mean, see, the point is, I mean, you assume some physics, the presence of some operator, and that does something. Whether that is something that you are interested in is a different question. But when you want to probe them, for example, I cannot probe this Weinberg operator at LHC. unfortunately, because there is no observable effects of this operator that can be produced in any signals of LHC. The only possibility is neutrinoless double beta decay, which we have not seen so far. And however, there are other effective operators that you can do. There are two reasons that we cannot do that, because it only couples to nu L C bar nu L. So, when you inflate the operator and write those terms, there is only one thing that it couples to is the neutrinos, I mean neutrino mass term, I mean that is the thing. So, you cannot produce anything else over that. And the second point is that the new physics scale, if you want to generate the neutrino masses, that has to be very, very heavy. So, the effects that it produces is also very tiny. So, higher dimensional effective operators are easier in that sense, because the limit on the effective new physics scale is a little less, and so the effects that they can produce a little more.
My question was different. I mean, when you go from one energy scale of an experiment to another energy scale, can I have the freedom of
Oh, Ajay, so
increasing
you
the-
want to, yeah, I think your question is that suppose if my energy scale is here, and then the relevant effective operators that can in principle contribute or can show up the deviation from my observables, whether that will enhance when I do enhance my energy of the experiment. This is something like that, right? Yeah, I mean in principle it is so, till when our new physics scale is actually larger. So, once we obey this limit, so basically you can say that when you have the lambda. So, the point is, I mean this is the operator, right, that you have, that this is C n O n, and this is suppressed by lambda to the power n minus 4, and there is a sum, let us put some I. So, now the first ingredient is that your lambda must be greater than E. This is the energy of your probe, right. I mean if your energy is above or close to that, the effective field theory description is no more valid. I mean it does not give you reliable results. But on the other hand, I mean within this regime, say for example, as this is an expansion in terms of lambda, or rather 1 by lambda. So, the operator contributions of 1 by lambda is more important than lambda 1 by lambda square, and then 1 by lambda to the power 3, and so on and so forth. So, being ignorant about what specific new physics that you want to probe, if your energy scale is low, then maybe this is the only one. Although this has another job of producing, say for example, neutrino masses, and it is being limited to say that there is a specific lambda and it produces vanishing results at the scale of your experiments. That's a different thing. But in general, your argument is true that if your energy scale is more, you can bring in or include, for example, you take into the dimension 6 effective operators for your some observables to Higgs physics. But then you say, okay, it looks like then the dimension 8 operator contributions are not also very tiny. So, you can bring in that at the 14 TeV center of mass energy. So, this is an argument which might be true.
So, the quick follow up, when we have,
yeah, maybe we should discuss it offline, because other people are tired and hungry and we should spare them actually. Yeah. Okay. So, so let us break now, and because it is already getting into 1. So, we gather here at 2:30 after lunch with Jose's lecture, and yeah, okay. So, I will come to you. Yeah. Thank you.
Okay. Okay, so you're going to ask the questions right now?
We will raise a green flag.
You will have to wait for the green flag? Okay. I can start? Thank you. Okay. So, welcome back. I'm going to continue where I left off earlier today. I'm going to remind you briefly that we're looking in this part at the effective theory that corresponds to the standard model as a low energy effective theory, assuming that the underlying physics is weakly coupled and decouples. Therefore, the appropriate expansion for the effective Lagrangian is in powers of 1 over lambda. I should say that later on in the course I will refine that further and to give a better estimate for the various coefficients, but at the moment the basic expansion is in powers of 1 over lambda. The notation that I went through, let me also remind you that there is no reason in principle to exclude charge conjugate fields, and so along the way, once in a while, such fields will show up. Okay, so and Shubha explained earlier today how you can construct those charge conjugate fields. I'll mention them in a little bit. Okay, so where I left off was in considering the dimension 5 operators, and I want to walk through this a little bit slowly to explain to you how one finds such operators. I will not do that for higher dimensions. It gets increasingly more involved, not more complicated, more tedious. And so I will not do that. Okay, so how does one go about constructing standard dimension 5 operators for the standard model effective field? So the operator general form has B scalars, F fermions, and D derivatives. I remind you that the gauge bosons are all buried inside the derivatives. So that's why they're not explicitly stated. I also remind you that in my case, phi will be the standard model doublet with the quantum numbers here listed. Or, if needed, it's charge conjugate. All right, so I want a dimension 5 operator. So using dimensional analysis, that means that B plus 3/2 F plus D equal to 5. So I should explain earlier why you have a 3/2 here, like that. The dimension must obey this linear relation. Moreover, every fermion appears with another fermion, otherwise you violate Lorentz invariance and angular momentum and all sorts of Poincare invariance. And so F must be even. And since you have, and B, F, and D are all positive. So the only way you can satisfy this relationship with F even is if F is 0 or 2. Because if F happened to be 4, then you would have here 6 plus B plus F equal to D. And that's impossible because B and D are greater or equal to 0. And you already have 6. And so this equation, this Diel-Fontaine equation can never be equal to 5. Okay. So F is 0 or 2. Okay, so let me consider them, and that's what one does. One does, you know, one case at a time. This is I'm going to write on the board.
You are unmuted, ma'am.
So let me take first the case F equal to 0. So there are no fermions. So I have an operator that has only scalars and derivatives. And by this equation, B plus D is equal to 5. So one or the other of these numbers must be odd, because the sum of 2 even numbers is even, and the sum of 2 odd numbers is even. So one of them is odd. So let's suppose that B is odd. Then I have an odd number of isoscalar doublets, either 1 or 3 or 5. It doesn't matter. I know there's a limitation. It cannot be more than 5. 1, 3, 5. But and this operator has to be gauge invariant. D doesn't carry an isospin number. And so, and when I talk weak isospin, I mean the SU2 gauge number. But out of these guys, you can never make a singlet. So this operator with odd number of B fields can never become a gauge singlet just because of the group theory. And therefore, it is forbidden by gauge invariance. The case where D is odd is even easier. So this doesn't work. D is odd. That doesn't work either because now you have this guy. Each of them carries a Lorentz index, mu, nu, alpha, whatever. And now you have an odd number of them. And no matter how you contract them, there will always be one left over. And so this operator would then be Lorentz variant, would not be a Lorentz invariant operator. And so it's disallowed, violates the symmetries. Thus disposing of the case f equal to 0. Our operator, if it exists, must have two fermions. So let's look at that case now. So now we have something that looks like this. And I'm going to erase the other two possibilities. Oop. So now, because f is equal to 2, b plus d is equal to 2 as well. From this equation, f is equal to 2, b plus d is equal to 2. So there are three cases, 2 and 0, 1 and 1, 0 and 1, and 2, sorry. And I'm going to consider them separately. So let's consider the case b equal to d equal to 1. Okay, this one here. Well, this is a little bit more complicated. So what do we have? We have one scalar isodoublet, one derivative, and two fermions. There are two possibilities. Either, I'm sorry, no possibility. There's one possibility. I want to maintain Lorentz invariant. So this guy has an index. Someplace else in the operator has to be an index. There is only one place that can show up in a gamma matrix. I cannot add any other field. I cannot add a derivative because D is 1. The only place it can show up is with a gamma matrix. So it must look like this. So to write that in the usual way, it's going to look like this. So these guys must have the same chirality. They must both be left or they must both be right. Okay? If they are left, they are isodoublets. And then you have 1, 2, 3 isodoublets from which you cannot make a singlet. Violates Lorentz invariance. This doesn't work. If you have two right guys, they're isosinglets. And now you have one isodoublet, of which you can now not make a gauge invariant object. And so by gauge invariance, this guy doesn't work. In fact, since these were the only two possibilities, B and D equal to 1 is disallowed, gone. So that's why it says there that it violates gauge and or Lorentz invariance. The violation of Lorentz invariance is if you decide not to put a gamma matrix here, then you have a dangling Lorentz index. You might, in that case, you can have a doublet, and a singlet. You can make a gauge invariant object, but you have a dangling Lorentz index. If this is a doublet and this is a singlet, this is left-handed, this is right-handed, there's no gamma matrix in here. Or there's two gamma matrices in there, it doesn't matter. And in other case, you have a dangling Lorentz index. And so you violate Lorentz invariance. All right, the next case. B is equal to 0, D is equal to 2. There are no scalars now. And now I have D, psi, psi. Okay? So how can I make that a Lorentz and a gauge singlet? Well, I could contract these two guys. And then I have psi by psi. But in that case, one of these guys is left, and the other one is right. One is a doublet, the other isn't a doublet, and therefore this violates Lorentz gauge invariance. The other possibility is to have something like this. Applied, okay. The derivatives can be both hit one guy or the other guy or one each. It doesn't matter. The point here is, again, chirality and gauge invariant. Since these guys are, there's two gamma matrices, they have the same, they have opposite chiralities, either left or right guys. Sorry, one left, one right. And again, you have a doublet and a singlet, or a singlet and a doublet, and this guy violates gauge invariance as well. It doesn't matter. The derivatives can hit both one guy or one each. It doesn't matter. The point is the chirality and the connection between left-right and isodoublet, isosinglet. So now this is dead too. And we are left with one possibility, just one possibility. That is where B is equal to 2 and D is equal to 0. No more derivatives. Yes?
You could write and allow only one term, but that will be total derivative, right?
One what?
One allowed term you could write, but that will be total derivative.
Total derivative. Yeah, total derivatives I don't. It doesn't. Those are not interesting.
Gauge invariant term.
The gauge invariant. Yes, exactly. Yeah, I'm not looking at those. And so the winner is B is equal to 2, D is equal to 0. Ta-da! 2 fermions, 2 bosons, and no derivatives. So O must look like phi, phi, psi, psi. And here, I'm not going to go through all the possibilities. It's just going to take a while. So the only thing that's left over is this. 2 scalars, 2 leptons, where LC is the standard charge conjugate. And phi tilde is the standard charge conjugate for the scalar field. And that's it. As Shubha mentioned earlier, this was originally discovered by Weinberg, and therefore it's often called the Weinberg operator. It's actually a class of operators because you can have a family index on each of the leptons, so it's a class of operators. And the other thing to notice is that you have an L and an L charge conjugate. This object violates lepton number by 2 units. It's a necessary lepton number violation. So if you include this in your Lagrangian, of which you're perfectly free to do, it satisfies all the local symmetries, you're tacitly assuming that the underlying physics in some way violates lepton number. So this necessarily is a lepton number violating operator. Now, what kind of new physics can generate this? Well, you saw some examples this morning. there are three possible ways of generating this object at tree level. They're called the seesaw, various versions of the seesaw mechanism. Cleverly called seesaw number 1, seesaw number 2, and seesaw number 3. But there are an infinite ways of generating this at loop level. And I will give an example of this later on in the course. This O5 has generated, for one, you would think, I mean, this is just one operator has generated so many papers, you would be astonished by this thing. It has thousands of papers have been written basically on the effects of this operator. And that's because of its connection with neutrino phenomenology. It generates neutrino Higgs couplings, but that's, we hardly we had such a hard time seeing one Higgs. We can't see any neutrinos. We just see their effects, right? And now we have, this is like, the blind leading the blind. So the fact that this operator generates this thing at the moment is an interesting fact, but it's not something that we can in any way probe with the current precision that we have. But when spontaneous symmetry breaking occurs, this guy gets a veil, this guy gets a veil, and what this generates is a term that's quadratic in the neutrino fields. These are the standard model neutrino fields, left-handed. The reason you can make a Lorentz invariant object is that you allow for the complex conjugates to occur. This is a Majorana term, a Majorana mass term, and it created, and it is that which has created so much interest. If you look at the models that generate this at tree level, then the Majorana mass that's produced is of this order, P over lambda. Well, V is the standard model vacuum expectation. I'm sorry. Should be V squared. It has a mass, so it has to have units of mass. So it's a constant times a V squared over lambda. I apologize. V squared, okay? V squared. I cannot correct it here because if I use the pen, this computer will stop working. So I will not choose it. I will not choose it, touch it. So V squared over lambda. 1V from this guy, 1V from that guy, 1 over lambda, because it's a dimension 5 operator, and a coefficient. So, since neutrino masses are teeny, either lambda is very large or C is very small. These are two possibilities. One likes to have rather natural coefficients, that is, coefficients that are not inexplicably small. One tends to think, and this is a prejudice, that very small coefficients are produced occur, if at all, for some reason. And there's no reason one can think for C to be very small. So people consider models where lambda is very large, 10 to the 15, 10 to the 16 GeV. But in addition to that, this operator violates lepton number. And so it has a possibility of explaining the matter over antimatter abundance in the universe by a mechanism in which, by a rather complicated mechanism. So very early in the universe, this type of interactions, so the physics that generates this guy's underlying, generates a lepton asymmetry, that is more leptons than anti-leptons. And then a standard model process that occurs around the symmetry breaking time, when the temperature of the universe dropped below 250 GeV, transforms that lepton asymmetry into the baryon asymmetry, and therefore we're here. Without that, we would not be here. And so an existential problem for us, and for all the universe that we see, I think it's sufficient motivation for studying models such as this that explain it. going through the whole phenomenology of this is super interesting, but that's another course. I mean, it really takes another course to do that. So that's what we have. Any questions about the construction? Yes?
In online there is a question, does this operator also changes the physio of scleron?
Change the?
Physio of the scleron.
Oh, yeah, so, okay, that is yet another course. So the operator at the moment, this operator is a low energy operator. It talks, it interacts, okay, there are many models. The model that, the simplest model involves heavy right-handed neutrinos. And so in no way that type of new physics talks to the quarks and baryons. However, once you come to sufficiently low energies, there are processes, non-perturbative processes that are associated with a classical configuration, unstable classical configuration, the standard model called the sphaleron. And it is through the interaction of that configuration with the leptons and with the quarks, which is rather complex, that the lepton number is transferred into baryon number. Was that the question? Is he happy or she happy? Smiley face? Okay, I'm good. I can, okay, thank you. Okay. All right.
One can sleep.
What's that?
One can sleep.
Okay.
He can see us.
Oh, we cannot see them.
No.
Okay.
But he can see.
He can see me. Okay. I cannot hide. Okay. Dimension 6 operators. So in order to construct dimension 6 operators, you go through the same process. You write it like this. And now in this case, b plus 3/2 f plus d is equal to 6. F has to be even, can to be 0, 2, or 4. If f is larger than 4, say 6, this equation cannot be satisfied for positive, for non-negative b and d. And then you go patiently considering all the possibilities. You might say, this is very tedious. You'll be very right. It is very tedious. But you do it because it provides a window into new physics, and you want to try to understand new physics. And so you just do it. Right? Or in the best case scenario, a friend of yours does it. And then you don't have to do it, you just copy it, which is exactly what I'm going to do. The only thing to remember, another thing to remember is you're allowed to include charge conjugate fields. And the other thing to remember is that the field strength tensors, they can be written in terms of terms quadratic in the derivatives, because the commutator of two covariant derivatives gives you a field strength tensor. Okay, so that's something to remember when doing the construction. Okay. Lastly, you eliminate these operators that coincide when on shell, and you get this rather uninspiring list of operators. And this is only the first slide. Okay? So they are listed in the kind of in classes. These are guys that have 3 or more vector bosons. These are guys that have only scalars or derivatives of scalars. These are guys with 2 fermions and 3 scalars. 2 fermions, 2 scalars, and a derivative. 2 fermions. No, you can figure it out. Like that. Let me just mention that many of these operators you may have met in the sense that they produce effects that are regularly talked about, like the raw parameter or the oblique parameters, which are good probes or are good probes of new physics. Other operators here correspond to those that would alter the neutron electric dipole moment. They violate CP, such as this guy here at the bottom and this guy here in the middle. They violate CP. p, and they would contribute, especially this guy, to the neutron dipole moment. So the point here is that the effects of many of these guys can be severely constrained, and however, of many others, the effects are completely open. We don't know. It's an ongoing process to measure them. The last thing I want to measure for this slide is, as you see, there are little indices here, Q, R, P, T, and so all these things, those are, I remind you, are the family indices. So there is no prohibition here in mixing families. And you might say, well, wait a minute, that generates flavor-changing neutral currents, and that would be true. And therefore, the data from flavor-changing neutral currents limits the effect. It puts constraints on the coefficients of the corresponding operators. Okay. Right. The type of effects that their various operators involve are not evident because I haven't written them in the unitary gauge. I've written them in a general expression. When you write the Higgs field here, the Higgs doublet, as VEV plus H, where H is the physical Higgs field, then these operators take a rather more familiar form. And for example, this particular set of operators from here modify the coupling of the various fermions to the Z boson. This operator at the bottom here modifies the couplings of the quarks to the W boson. Okay, those are things. So I'm just displaying them in their gauge invariant form. In practice, when you're looking at the phenomenology of any one of these operators, you write it out in terms of a physical basis and see what you get. Okay. These operators, all of them, have many terms. Many terms. You expand them in all the terms. Each term produces a vertex. Each vertex can contribute to a Feynman graph, included in a cross-section, in a loop, whatever you want, doing the calculations in standard fashion with a new set of vertices. The other thing to remember here is that those vertices, many vertices might show up, but those that come from the same operator, the vertices, the coefficients of these vertices are all correlated. So this guy, for example, this term here, this is the field strength tensor for the gluon field. The field strength tensor for the gluon field, I'm going to write down. I'm just reminding you. So G mu nu has a term that goes like this, and then has a term that looks like this: G strong, F A B C, G mu B. That is, has a term linear in the gluon fields, has a term quadratic in the gluon fields. So my friend here, Mr. Neutron electric dipole moment, friend here, has 3 field strengths. So we'll have terms cubic, quartic, quintic, and sextic, power 6, in the gluon field, whose coefficients are all correlated. It comes from this expression here on the board. Right? Some of them have extra powers of GS, and they might come out with particular numerical coefficients. Those are not for you to change. The numerical coefficients are mandated by gauge invariance, and you cannot, I mean, you can change them, it's okay. But if you change them, you're violating gauge invariance. So those are fixed by gauge invariance. All right, sons, I already bored you with this. Let me bore you more with the other guys. Okay, these are the slew or 4 Fermi operators. Ta-da. In all, there are 59 operators, assuming only one family, that is ignoring the family numbers. I have not bothered, nor will I bother, nor do I encourage you to bother, to count the operators when you include all possible family combinations. I think many summarizes the thing. I also did not include baryon number violating operators. And there's a good reason for that. There is no indication of baryon number violation. The latest data, I think, for the lifetime of the proton is 10 to the 32 years, 10 to the 31 years, which if you count, that is a long time. That means that the decay time of the proton is very long. The width is therefore very small. And that implies that any contribution to the width must be very small itself. These operators must then produce tiny, whiny, teeny, very small effects, which means that the scale, the lambda, that is associated with them must be very, 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 very large. And therefore, since there's no effects, I'm just didn't put. Okay? Here they're classified according to what shows up. These are all left-handed fermions. Here are only right-handed. Here's left-right. And here's another version of left-rights. I often will refer to these guys as a vector exchange, just because you have a gamma mu, and you can imagine a vector connecting this current with this other current. Okay, the same thing here. I'll call it vector exchange. The same thing here, vector exchange. That's not necessarily true. I mean, because of Pierce transforms, in some cases, these operators might be generated by scalars. Okay, but I will still often refer them in unguarded moments. I will refer them as vector exchange operators. And similarly, I may call these guys scalar, or in this particular case here, that is a sigma mu nu tensor exchanges. Okay, but just keep in mind that that's just a label. It doesn't necessarily imply, especially in this case, that this operator you should never consider, because we have not seen any antisymmetric tensor in nature, so why bother with this guy? In fact, this operator can be generated by other particles, more common particles, vectors, scalars, through a Pierce exchange. A good exercise, for those times that you cannot sleep, is to derive the B violating operators. There are not that many, and gives you an idea of what possible, very high scale new physics can produce at low energies that we might be able to probe in future experiments. All right. So, when you're trying to use this thing in a reaction, so what happens often is that Atlas or CMS decide that they're going to look at something else. 3 top final states, 7 big plus 7 big quarks or something like that. That might be somebody's thesis, might be something that the collaboration is interested for one reason or another. And then one of the things that they do often is they recruit a theorist like us to try to find out what kind of physics beyond the standard model would be probed and what kind of sensitivity to that new physics would come from their measurement. And so either you or the collaboration or your advisor finds a reaction of interest and to look at. And then the process is very straightforward. You find the dimension 6. I'm just using dimension 6 operators because most of the processes you will look at are affected by dimension 6 operators. You find those that contribute to the process of interest. You derive whatever relevant observables are needed, cross-sections, decay widths, whatever. And then you compare with experiment. And from it, you find deviations. And if not, you find limits that constrain the operators at hand. And then you repeat. At the moment, there's no discovery of deviations yet. So we're still doing this little circular thing. You might think that this is kind of rather uninspiring. That's because of the way I've described it. It's not that you just go and say, okay, now I'm going to look at reactions with one top. Okay, no effects, I got my limits. Now I've got reactions with two tops. I'm going to like 3 tops, 4 tops, gets more. There's a little bit more than that. There is some certain amount of prejudice, some certain amount of understanding of various possible physics underlying the standard model that might motivate the choice of one type of reaction over another, of one type of operators over others. So there is, it's not mechanical. Obtaining the limits is as doing any calculation. That is mechanical. Right? Finding what calculation to do, which is of interest, that is certainly not a mechanical thing. But still, we're very sad that no effects beyond the standard model have been detected. Okay, so now I'm going to briefly mention the yet higher dimensional operators. And in fact, you can go through the same, there's a point of why I'm mentioning them. You can go through the same process as with dimension 5 operators, dimension 6 operators, and you get these guys, 20. And this is kind of a pattern that repeats. The dimension 5 is 1, dimension 6 is 60. Dimension 7 is 20. Dimension 8 is very many. When dimension 9, it's not very, very many, but just many. Okay? So the odd number, operators with odd number of dimensions seem to be less of them than you might expect. Why that happens, I don't know. But I also don't know, it's tantalizing, is that all 20 operators in this list violate B minus L. Why should that be the case? I have no idea. And okay, but it's just so. It depends crucially on the content, the low energy content of the standard model. If you imagine adding to the standard model a singlet scalar, just one singlet scalar, has no quantum numbers, just a scalar, boring. Then you can then write down dimension 7 operators that don't violate B minus L. That's really trivial. The only thing you have to do is take my previous list, and for each one of these guys, multiply it by the scalar. Each of these guys is gauge invariant, and I multiply by gauge invariant object, S, my scalar. And so I add one dimension, and they all become dimension 7. But the fact is that the standard model does not have a scalar like that. And so the dimension 7 operators that I'm listed here are the ones corresponding to the low energy physics being the standard model, and they all violate B minus L. But why bother? I've been telling you, larger dimension, lower effects. We're already having no effects with dimension 6, and now I'm telling you to go and look at dimension 7. Well, the reason is that this provides the next, the not dimension 5 L violating operators that come up. There's also dimension 9 operators that violate L, but I will come to those in a minute. So because these are L violating and B minus L violating operators, they have a certain amount of interest. And then we come to the next frontier, operators of dimension more than 7. You can find, actually it's instructive to look at those papers. They have tables with lists of operators. I mean, and there's hundreds and hundreds and hundreds of operators in this thing, and they're all listed there. and they're just listed. They're just lists. I guess they're written because the authors could do it, but to be honest, I don't see the point in going around and listing all operators. What I'm trying to say is don't think the fact that there's no dimension 10 operator list as an opportunity for research. This is not to do. The only reason you might consider operators of dimensions higher than 6, in fact, is because there are specific processes to which these guys contribute and to which no other one contributes. So they're targeted. And in that case, you're not interested in all operators of dimension 17, but just in the one guy that contributes to the one process of interest that you are looking at. Okay, so looking at trying to generate all of them, it's a demonstration power, calculation of power, and things like that. But in practical applications, you don't do that. You find the operators that are relevant for your process, and then you work with those. And this is the intent of this last comment here. When I look at my version of effective theory in neutrinoless double beta decay, I'll give an example. In that case, I will need a dimension 7 operator, and I will need a dimension 9 operator, but that will justify the need when I come to that time. And it's only one operator for each. There are software programs that very cleverly generate all the operators at any loop at any order that you might need. So now actually sitting down and writing them down becomes even more of a. I think people have better things to do now that we have computers to do that for us. Any questions? Okay, if not, let me start with the next topic. I have a few minutes, and talk about, start with applications. I will have some applications, then I'll go back to some formal talk about discussion on the properties of effective field theory, but I think it's a good time to take a break of all these abstract things and look at some specific application of the formulas. There are many ways of many processes to which the effective theory operators contribute, many, of course, all of them. Okay? But in many cases, the problem we face is that the standard model produces a huge signal, and we're trying to find buried under it some effects of new physics. In principle, if we had enough statistics, that could be done. In practice, we don't have enough statistics. So what one tries to find are processes where the standard model is either absent or strongly suppressed, and where the effects of new physics can shine through without too much interference. And I'm going to show you one example to begin with here. So this is a rare standard model effect. I'm going to look at it. And I'm going to imagine I have an E plus E minus collider. Now, I know we don't have any E plus E minus high energy colliders anymore, but we used to. So maybe in the future we will yet again have one. Okay. So this was a calculation done for LEP, the last large E plus E minus collider. It can be easily extended to planned colliders like CLIC or the ILC, but I will not do that. I will just give you the calculation for LEP. So imagine that you have an E plus E minus machine, and you're looking at processes where there are n B quarks in the final state, plus something else. X can be anything except no B quarks. And by B quarks, I mean B or B bar quarks. Just that kind of thing, just no B. Now, In the standard model, the third family mixes with the others, and there's a point for saying this. However, the mixing angles to the third family are small. These numbers might be updated. So these are relatively old numbers, but they will not change in order of magnitude. So the point is that in the standard model, the third generation almost does not mix. So, because of that, the number of quarks in the third generation does not change from initial to final state. In the initial state, I have no quarks at all. So in the final state, I will have to have an equal number of third generation quark anti-quark pairs. It can be B bar, B T bar, TB bar, and so on. Okay. I am going to assume also that I don't produce T quarks. That was true for the LEP calculation that I did because the LEP didn't have enough energy to produce a single T quark. It just didn't happen. So in that situation, since I have no quarks here, and since quark of the third generation do not mix with the others, okay, to first order, to first approximation, setting these guys equal to 0, this number, little n, has to be even. I have to produce an equal number of B and B bar quarks. Once you include this, that's no longer true, because a B quark can oscillate into a C quark, and now you can have a B bar C in the final state, for example. Right? But the amplitude for that is very small. It's suppressed by a CKM angle, so it's small. Okay. And that's the idea. The standard model cross-section for this, when n is odd, will be small. And so it allows the possibility, provides a window for probing violation of this approximate discrete symmetry of the standard model, approximate in the sense that it's broken explicitly by these angles. Probing that affects, new physics effects that might actually violate the symmetry relatively, without any suppression, I should say, relatively largely, strongly, without any such suppression. And that's the idea. So with that, there is this approximate symmetry, which is -1 to the number of B quarks. That has to be even for the process at hand. So each state, you can say it has ZB equal to 1 or -1 according to the number of B quarks in it. So this is what I just said. And so this process is in fact very rare in the standard model. And so new physics effects that violate this are easier to observe. And that sounds straightforward and everything. The reality is a little bit more complicated because even if the standard model cannot produce this at a significant rate, experimental error can certainly do it. So saying I have found n quarks of any one flavor is complicated. Within an experimental setup, there's an efficiency for identifying quarks, and which is not perfect. And there's also a probability for mistaking quarks of a different flavor as B quarks. And all that has to be taken into account. LEP was a fantastic machine. It operated for many years, and they understood the detectors at LEP very well. And so by the time the experiment matured, then all these probabilities that I'm telling you about were very well known. How much of chance you have of producing a C quark and having your software identified as a B quark, mistaking it for a B quark. The probability for that is known. Similarly, the probability for the other way, that you have a B quark and mistaking it for some other type of quark, the efficiency for finding a B quark, that was also known. And so on. and those kinds of effects could not be ignored. So if the probability of making mistakes were all zero, then it would be just straightforward calculation. I think otherwise you have to include those effects. Like this. So instead of considering simply producing n big quarks, I'm going to imagine I produce m c quarks and l light quarks. That means strange up or down quarks. Okay. Then the cross-section that you actually measure is a funny combination of all the ones for this production, for this final state, because you may screw up and misidentify a B quark, screw up and identify a C quark as a B, or identify a light quark as a B as well. And this thing is the cross-section then that you miss. This is the probability of actually identifying a B quark, U of them. Okay, U, V, and W are integers. U of them you identify correctly, N minus U of them you misidentify. V of these guys you mistake. And M minus V you don't mistake as B quarks. And similarly for the light quarks. And this is a combinatorial factor. And the sum is all this. And I just confused you a little bit more because I'm detecting KB jets instead of N, and I apologize. So I'm looking at final state where my software says you have found KB quarks. That is not that I have KB quarks. It has a certain chance of having different number of B quarks, less than K, but different number of actual B quarks, and mistaken C quarks and light quarks for B quarks. And you have to take all that into account. You do this, and this is the cross-section that you're interested in measuring and calculating. Any questions about this? This is a little bit too much phenomenology, but really, you really have to do this. Otherwise, the results, I mean, you just get results that are not taken seriously. They're not relevant for the experiment at hand. All right. Oops. And now we have errors and backgrounds. So this is a, let me call this NKJ, is the total number of events with KB jets and J total jets with K odd. So this is calculated for this, it's that type of construction where N plus M plus L is equal to capital J. And if you want to have an exclusion limit on the type of new physics that might produce this violation that I'm talking about, you want this condition to have. The prediction from the standard model minus the prediction of your theory, that is standard model plus effective theory, has to be 3 times larger than an error. This is the 3 sigma condition. This error is a sum of 3 errors. The easiest one is a statistical error. This is the square root of n error that you're familiar, hopefully, from statistics. So yeah, you put it in here. This contribution is n. I'm assuming that error and the others are uncorrelated, so they add in quadrature. The other term here is a systematic error. That is a problem of the experiment. Those were calculated by the experiment and told by us. These are not something a theoretician calculates. Just you need to know the experiment in detail. So this we get from lab. And that theoretical error has to do with effects that we did not take into account. QCD, these are quarks. So there are QCD effects to take into account, mainly. That's the main effect. And we parameterize that, a term linear in the number of particles, a number of events that number of events that we produce times some quantity delta t. I'm running out of time. I won't finish. So let me tell you what the new physics is, and then tell you what's going to happen, and then finish. So there are many operators in the list that I showed you that violate the ZB. Many. And we chose one, a 4 Fermi operator. Random. And this operator has the virtue that it has 2 leptons, in particular have an electron and a positron in one factor here. It has 2 quarks in the final state with flavor labels I and J. So what we did is we took I to be 1, that means the first family, or 2, and we took J to be from the third family. So this would violate this ZB symmetry because the operator has a single object in the third family by assuming this is in the first or second family. Okay? I think we took the first family. You might say, well, that's contrived. In a way, it is. But what's what we're trying to prove? To probe types of new physics that generate violation of this ZB thing. Okay. There's plenty of physics that do this type, that generate this type of effect, and would generate this operator at low energies. And you might have noticed I forgot to put a C here. I did forget to put a C here. I apologize.
So
yeah.
this operator has generated, you have written this, it is generated by a heavy leptoquark.
I'm sorry?
This operator.
It can be generated by leptoquarks? Yes, certainly can be generated by leptoquarks. It can also be generated by Z prime with flavor changing couplings. Okay, so the question is what could generate this operator? I could generate this. I'm going to write the things that can generate it at 3 level. Okay? So could generate, so what do you have? You have 2 leptons and 2 quarks coming in. Yeah, 1 quark and a quark. Yeah. So, for example, it can be generated by this type of diagram. Okay. The catch is that this vertex of the Z prime to the quarks must somehow violate flavor. It must have first generation here and third generation here. Okay? There are limits. There are limits on this type of coupling. Yeah, there's limits on flavor changing neutral currents. The limits involving the third generation are weaker because it's just harder to measure. Well, at the time. Now it's better with the various B experiments. But there's another one that you mentioned, of course, this. And this is less problematic in the sense that the only thing you have to do is assume that there is, remember, this is an E plus E minus collider. So this is first generation, and say first generation guy here, and this is first generation and third generation. So you have to assume you have a leptoquark. In this case, it has to be a vector leptoquark so leptoquark that couples, as its name indicates, leptons to quarks, which also has flavor changing couplings from one generation to the other. Okay, so those are the the two possibilities. Once you allow the thing to be generated at loop level, the sky's the limit. There's many operators, there are many processes that can generate this operator through loops. It's more complicated.
No, another point is like suppose we have written this operator in the mass basis.
In the?
Mass basis.
In the mass region?
We have written this operator in the mass basis, right? In this operator, that is Q, the quark only. This is not the doublet or.
No, this is the doublet. These are all doublets. This is the standard. L.
Yeah, L for.
L.
Isodoublet.
L is the isodoublet. L is, in our case, electron, neutrino, electron. And quark is up left, down left. Quark left, down left. So this operator, in fact, generates in itself many vertices. Okay, so that would be, 4 vertices. It has a neutrino, quark has a electron. Okay, neutrino, up, neutrino, down, E plus E minus, up, E plus E minus, down. Yeah. Thank you. Other questions? Okay. I apologize for over.
Yeah, Jose.
Yes.
Why this leptoquark has to be vector boson?
A vector?
Why
Yes.
this?
Why does it have to be a vector boson?
Yeah, not scalar.
In order to get this operator, this operator looks like this. Yeah. From a leptoquark, you would have to use a Fierce transform, right? A Fierce transform. So this guy generates something like L bar times Q.
Okay.
And a Q bar something L. If the leptoquark is a scalar, this is 1. If the leptoquark is a vector, this is gamma mu.
Yeah, got it.
And what happens is that when you do a Fierce transform, only the vector one will change left into left, that kind of thing. It's just a feature of the Fierce transform. Other questions? All right, thank you. I will see you tomorrow, and we can have tea, right? Yes. We have tea. All right. Thank you.
a little bit about the renormalizability in standard model. So, okay, not at all? Okay, so he disagrees. Okay, but he is going to talk about the renormalizability in QED for sure, so that will be also eliminated. Okay, so with this I think, yeah, the stage is Sanjoy's. And Sanjay hates those pads. Actually, that doesn't work. So we have to use the green board. Yeah.
I hit nothing. Hello, can you hear me? Yeah. Okay. Just first, thanks Subhaditya for this opportunity, and also I'm little scared. Whatever he has said that I have to explain, I'll not explain anything. Okay. And the next thing is that I'll be saying elementary things which all of you already know perhaps, so just a repetition maybe. Okay. So don't worry. I'll be saying very simple things, not even renormalizability of the QED. Okay. So forget about standard model. Okay. Again, I'm afraid of giving the title of this lecture, so there is no title. Okay. So it's just I'll be doing some loop, just illustrative example. Let's say one loop calculation in QED context, and then try to explain what it means by renormalizing something. Okay, the field and couplings and all that. And let's see how far I can proceed. I may be ending up at the middle of nowhere. Okay. So don't worry. Okay, so again, let me give this thing that is, I think I have to write little big. Renormalization of QED. Okay. So my starting point will be this particular thing that we use or that we compute in an interacting quantum field theory, okay, which is this thing, the endpoint correlation function, time ordered, okay. And this quantity can be calculated in an interacting quantum field theory, where your is this visible? Okay. Yeah. So in a interacting quantum field theory, if you have a free part of a Lagrangian and the interacting part, you can compute this quantity in perturbative quantum field theory, order by order. Okay. The thing that I'll be interested in for the moment is this particular quantity, which is the 2-point correlation function of let's say electron, or the Dirac involving Dirac field. Okay. And in the context of QED, so my L is I think I can write it here. So my L is the QED Lagrangian, okay, which is minus 1/4 f mu nu plus psi.
The chair is not for you, but for the duster.
Yeah, okay, thank you. Okay, so this is the Lagrangian, and this is my L interaction. if you recall that the expression that I wrote earlier, that in perturbative quantum field theory we can calculate this. There is a, in terms of the interacting field, in terms of the field of in interaction picture, and calculating this time order product of those field in interaction picture in a free theory vacuum, right? But the effect of all those things, which I do not want to write right now, those big expression, is basically this result will be sum of all the diagrams with two external lines without the bubble diagram, right? Okay. So if you draw the diagrams in the context of QED, this will be given by all these diagrams. Okay, let's say this is x, beta, alpha, and so on. At higher order, you will get all these other diagrams. Okay, let me just draw maybe one more. This will be another diagram at higher order. And so on. Okay. Many other diagrams, there will be two more diagrams at this order, okay, and then higher order diagrams. This thing can be systematically written down using this notion called 1PI diagrams, one particle irreducible diagrams, which all of you perhaps know. So these are the diagrams. If you cut any internal lines of those diagrams, it doesn't give you two separate diagrams. Okay. So I'll just introduce this diagrammatic symbol. Okay. By the way, let me give this quantity a diagrammatic notation again. So I'll be giving this with a blob. Okay, x prime beta, x alpha. By the way, also I have chosen a arrow convention, okay, to draw this diagram. So these are the diagrams which are actually this particular diagram will be sum of all one particle irreducible diagrams. Okay, so these are basically collection of these diagrams. Okay, I am not putting the indices. And so on. These are all one PI diagrams. If you cut any internal line of these diagrams, they don't give you two separate diagrams, right? So then this expression that we have, this diagrammatic expression of this 2-point correlation function, you can actually write it in this way. Okay, just let me use this quantity. So this thing you can write it down, which is this 2-point correlation function in interacting theory. You can write it down in this way. Right. With two insertion of such 1 PI contribution and so on. So this will get repeated. Okay. You can just I think either you already know, if you do not have done this thing, you can just go back and put this thing together. Okay. So, let me write down the amplitude of this particular diagram. Okay. So, this diagram has also, okay, before I do that, this is a position space. Any question? This is a position space diagram. I will just, since I will be only interested in momentum space amplitude, let me give the corresponding amplitude in momentum space. Okay. So, for example, this quantity, let us say, if I draw the same diagram in momentum space, there will be labels, the momentum labeling, okay, in all of this and so on, and this whole amplitude I will be writing down using, so this I have to put using this Feynman rules in QED. I have to put all the factors. This is a propagator, this is some amplitude which you will be seeing what it is actually, and this is another propagator, and these are all free, this propagator all free theory propagator. Okay. So, and these are the diagrams in momentum space. So, let me put all this. So, this quantity is the, I am just writing down the, sorry, I am just writing down the amplitude of this whole thing. Okay. I sigma p times SF tilde. So, there are these two propagator on both sides, and this basically represent the amplitude of this kind of all these loops that are there. If you just kind of input this external legs, this will represent that part. Okay. So, yeah. So here I have the same thing repeated many times, so it will give a geometric series, right. So, one can sum that formally, because ultimately those things we will see, we will have some certain we will have divergences. So, so this sum will be a formal sum in the sense that when you do actual computation, you do it in a regulated theory, not in a theory where this is with bare parameters and bare couplings. Okay. So, if I call this, if I give this full propagator in the interacting theory a name, so this will be the in momentum space, all these thing will be replaced by a momentum label. Okay. So, the momentum space 2-point correlation function, okay, the full theory correlation function, this quantity will be related to the free theory propagator and this additional contribution. Okay. So, you can sum this whole contribution in a using this geometric series sum, okay, and it will look something like this. I by p slash minus m naught minus sigma p. Okay. Up to this point, I think, is it okay? So, this m naught was the this bare parameter that appears here, okay, and sigma p one need to compute. Okay. So, this basically tells you that the pole of the propagator gets a shift by this amount, right. So, the basic task in any theory, for example, in this context in quantum electrodynamics, will be to calculate this quantity order by order. Okay. So, the first diagram that we encounter is this particular quantity. Okay. I will just write down the amplitude of this diagram. Let us say, so if we are interested in one loop renormalization of QED, okay, this is one basic amplitude that one finds to be divergent, one simple amplitude one finds to be divergence. It is a simple 2-point correlation function, and one need to see what is the how this quantity diverge, let us say at large momentum, which will be called which is called ultraviolet divergences, and how to regulate them, and how to kind of either cancel them or absorb them in the redefinition of the field and parameters. Okay. So, let us take only one diagram first, okay, this particular one. So, I will be interested only the contribution to this sigma p coming from this one loop diagram. Is that okay? So this is the order E squared diagram. So I will be calling that quantity sigma 2 of P. Okay. So my I just one more thing. Let me just finish this part. I just forgot to mention is this thing that the physical mass of the particle, okay, for example for the electron, is no longer this m naught. Okay, it will be given by the location of the pole in this propagator, in this 2-point correlation function. Okay, so let's say at p slash equal to m, this denominator vanishes, then the m will be the location of the pole. Okay. So the location of the pole will be determined, which will be also the physical mass. In fact, we will be taking that as a definition of the physical mass by the following equation, right? So it will be P slash, should be bigger, it should be where this denominator vanishes. So this is where, for which value of P slash this gives you 0 is actually the location of the pole. Okay. Another thing is related to this particular expression. Is I, there is a dot. Okay. The other thing is that if you try to expand this around this pole, okay, you can actually do that. The only thing since we have not calculated this, okay, this sigma p, okay, once we calculate we can check what kind of as a function of p how does it behave. So for the moment let me assume that this is at least near the pole, this is an analytic function of p. Okay, so one can expand that this sigma p near the pole, and if you expand this sigma p near the pole, okay, so it will look something like this: sigma of m minus d sigma dp slash. Okay, by the way, this is function of p slash. Okay, even though I am writing p at p slash equal to m, and so on. So this is just a Taylor series expansion, and it's possible if it's an analytic function. In general, it's very difficult to predict this analytic behavior of this thing. But only one, I think, one thing that guarantees that there will be a simple pole, there will be a particle like we can have a particle like nature in this thing. It's by this general principle that you use and derive this Kellel-Neyman spectral representation, where it actually at least gives you at least one pole, right, which corresponds to the mass of the particle, and then you might have bound state and other things. So as long as that is guaranteed, at least near the pole you can do a Taylor series expansion. Okay. And then if you just substitute this here, this quantity, this particular quantity near the pole will look something like this. So keep this relation in mind. This will look near pole, it looks something like okay, plus maybe some extra term. So now if it's just a substitution of this gives you this particular thing, and z can be also calculated. Okay, it's actually the residue at the location of the pole, and I'll call it, because this is historically called z2, so let me call it z2. Okay, and this Z2 has an expression. This is given by this 1 minus d sigma dp slash at p slash equal to m inverse. Okay. So, this comes if you substitute this thing. So, there are other terms, but if you just substitute this and ignore the higher the term that is proportional to p slash minus m square and other powers, you will have this behavior. Okay. And this is one of the things that will be most important thing in all the theories that we do actually. Okay. Whenever in the context of renormalization, okay, these are the quantities that we calculate. Okay. And later on we will see how these things will be important. Okay, if I can complete this whole discussion. Okay, any question up to this point? Okay, so the next thing that I will be doing, I will focus on this particular one loop diagram, write down its amplitude and try to maybe explain a few things, and also finally I will try to write down the amplitude without going through all the steps, but in case you have any question, you can ask me at this point. I can erase this Lagrangian maybe. So let's take this diagram. I think this one. So this is the diagram we are interested in. Okay. So let me give this momentum level of this internal lines. Okay. And then you have to write down the amplitude of this quantity. And so this is, let's say, SF in interacting theory, but up to order 2, okay, or at one loop, whatever you can think of. So this quantity is, so I sigma 2 of p, okay, which represents only this one loop 1 pi diagram, okay, and SF p on both sides, but this particular quantity minus I sigma 2 of p is the amplitude of the loop part only, okay, and it looks something like this. Okay. Just use of simple Feynman rules gives you this amplitude. There is this undetermined loop momentum which we should integrate over all the range, over the full range. Okay. I k slash plus m naught I k square minus m naught square plus I epsilon gamma mu minus I eta mu nu k square p minus k plus I epsilon, and there is a gamma mu as well, right? One extra. No, let me see. Did I miss it? Yeah, there is a gamma mu. There is one gamma mu. Yeah, I think it's okay, right? Yeah, okay, fine. Yeah. Two things that I should mention here is this. One is I am using the photon propagator in Feynman gauge. Okay, I'll quote the result in arbitrary gauge, and it turns out that the electron propagator, if we calculate in arbitrary gauge, is a gauge dependent quantity. Okay, I'll give you the result, but it should not be surprising thing that why a electron have a gauge dependent propagator, right? But we are talking about off-shell electron right now. It's a correlation function that we are calculating. If we do it for on-shell electron, it should not depend on the gauge. So the final result that we will see when there is a gauge dependent propagator I use for this photon, if I put on shell condition p slash equal to m, this should be there should not be any gauge dependency on that propagator. Okay, so that I'll come later on, but let's keep that in mind. One more thing I should also mention here is that all these integral that are there, okay, these are all in the full range from minus infinity to plus infinity, and so this thing is, maybe I just quickly mention this. What I mean by this is this particular quantity, and this is slightly crucial. All this integration that we have, this d4k over full range, I mean by this statement is this quantity. Okay, so dk0, dkx, and so on. So all of them goes to minus infinity to plus infinity, but in this way, not in another way. For example, not two different, let's say if you have lambda 1 and lambda 2, okay, and lambda 1 goes to infinity and lambda 2 goes to infinity. It's not in that way. Okay. In fact, if you use that, so this is already one kind of regulation that we are using. Basically, it's like Cauchy principal value we are using, because the theory has all this expression actually diverges in if you take lambda 1, lambda 2 and take them independently to infinity. In fact, if you calculate this in free theory, this momentum operator, if you recall, okay, and the momentum operator has this this particular integration. If you have seen it, there is this k vector and there is a delta cube 0. I think if you when you calculate this momentum operator in free theory, okay, this is a divergent quantity, this delta cube 0, and you have a k here, okay, and you use this argument of odd function and whatever, then you set it to 0 so that the ground state doesn't have any momentum. This is strictly not true if you use this kind of lambda 1, lambda 2 and take them independently, because this is not a proper integral. This is a proper integral only when you have the limit from minus lambda to plus lambda and take the lambda tends to infinity limit, okay. Then only it goes to 0. Otherwise, it's a completely improper thing to do. So we have this regulator from the very beginning in the quantum field theory, and it's always a regulated theory. So keep that in mind. So I have this integral in that sense, okay. So this will help me to drop the linear term later on, the term that is linear in k in this numerator, okay. In fact, I'll use this odd function analogy and I'll drop them, but that's strictly possible when you have this thing. But anyway, that I'll do later on. Okay. So you can see there are this expression, for example, has already two kinds of divergences. One is in the large k limit when the momentum goes to infinity, okay, the power of the numerator and denominator, in fact in this form it's one should not check it in this form, but just naively if I just say, you can see there is a k slash here, so the power of the whole numerator is, there is a d4k, so it goes like k to the power, so it goes like k to the power 5, the numerator goes, and then there is a k4, the denominator has a behavior for at high energy is k square and another k square here, k4, right. So it's like k to the power 5 and new denominator has k4, so it's quadratically divergent, right. But the linear term will cancel precisely because of this thing that I told. So ultimately we will see a logarithmic divergence in this, and we will try to regulate that. First of all, any expression that is infinity is not possible to formally manipulate it. The best way to do this, or maybe I do not know whether it is the only way or not, is you regulate the integral, okay, you manipulate it and find the divergent piece and the finite piece separately, and then later on whatever you want to do with those divergence piece, whether you want to cancel, whether you want to throw the theory or not, that's up to you. But let's first do this manipulation using some regulator, okay. So what kind of regulator one can choose? There are various possible choices, okay. I'll be particularly using dimensional regularization, but let me just give a simple example where you will, let's say where you have a similar such thing you encounter. For example, let's just consider Euclidean integration, let's say in 2 dimension, something like this. Okay. This also has, if you integrate over a whole range, it has a logarithmic divergences, right? So you can actually try to regulate this by maybe introducing a cutoff, sharp cutoff. Okay. This is already a Euclidean integration, so I can just put the some upper limit and go to the. So you can go to the. So there is 1 over 2 pi square. Okay. So you can go to this radial and angular part, okay, in 2 dimensional in 2 dimension, and it will look something like this. I hope I have it here. It will look something like this. D of p square. This is the radial integration that you are doing over 4 pi. Okay, 1 over p square plus m square, and the result is all of you know is ln lambda square plus m square, and this is one way you regulate this, and you get you can recover the divergent piece by taking this to again to infinity. Okay. One more possibility also that you perhaps all know is instead of this one, you consider a separate integration. So you subtract the infinity by introducing this thing called. So let me define an integral which is like this one. And you subtract from this another integral, which is just similar expression, but m is replaced by capital M square. Okay. So this is this actually called Pauli-Villars regularization. Okay. Effectively, what you are doing, this is a contribution that you are getting, let's say, due to some particle, okay, and you are getting a loop due to the let's say propagation of a scalar particle, let's say in 2 dimension, okay, and you are subtracting a similar contribution maybe due to other field, and its propagator also look like a scalar. Okay, the only difference is that the contribution comes with a negative sign, right? So in the context of Higgs, you have seen that the correction to the Higgs propagator for scalar contribution comes with one sign, and the Fermat comes with the opposite sign, maybe minus sign, right? So it's like opposite statistics, but it's still a kind of the behavior is like a scalar particle. Okay, it's not a physical particle, but you can interpret it in that way. Okay, and I think the result I don't know. It will go like something like this. Ln, ultimately this divergence will go like m squared by small m square. Okay, up to some factor. And it will also diverge if you take this m. Ultimately, it should decouple. So you should take this capital M tends to infinity limit, so that you have recovered the original integral, which was I. Okay, but then you encounter the divergence again. Okay. There are many other things, by the way, by which you can regulate this kind of integral, and you can look at this paper by Hitoshi Murayama. That's just a note where he discusses all other possible regulator. Okay, the one I will be using is the dimensional regularization in this context. Okay, so I will do this here, not in that simple example. Any question up to this point? I maybe not be able to complete this calculation either. Anyway, so the next you can do one thing. You can at least, because it's a divergent integral, you can maybe regulate it fast. Okay, but some simple algebraic operation you can still do. In a divergent integral, you are not allowed to do many operations. For example, you are not allowed to do shift and all these things. Okay, at this level, so you can regulate it and you can go ahead with the manipulations. But this manipulation we can do, the manipulation of the numerator and denominator, little bit. Let's say I can take product of this thing. Okay, I can do that. And the famous thing that we use is the Feynman trick to combine this two propagator in the denominator. Okay, using this identity. dx by ax plus b into 1 minus x square if you have such factor. Okay. So, let us say we combine this propagator using this trick, and then we also go to the d dimension. So, I will do all this together and write down the result. We also go to d dimension. So, it will be ddk and so on, it will be 2 pi to the power d. So, let me write down this expression. So, minus I sigma 2 p, it will be minus I square d d k by, okay. And let me write down the final result after. Okay. So, and if you go to d dimension, the dimension of this quantity, okay, whatever it has, you are actually kind of increasing its dimension by increasing the power of momentum integral. Okay. So, you should just take care, that can be taken care of by a factor of, let us say, dimensionful quantity. So, this is the arbitrary dimensionful quantity that we are introducing in it, and in fact I can give it a name in instead of this quantity, because I am calculating a completely different quantity in d dimension. Okay. So, it looks something like this, dx k slash plus m, and you combine all the numerators and denominators in whatever way, it will comes out to be k minus xp whole square minus some delta, okay, and plus I epsilon. So, now since it is a regulated integral, you can interchange these two integral, you can redefine your momentum integral or momentum integration variable by a shift. You can call this to be new momentum variable or integration variable, this k minus xp. Okay. So, this is now allowed because it is a regulated integral already, and this delta is this particular quantity. But this delta is m naught square 1 minus x into 1 minus x p square. Okay. So, let me just define this thing shift, okay, k prime equal to k minus xp, and if you do that, I can replace this with k prime square. This is d4 k prime, because under this dd k prime, sorry, and this shift also gives the extra contribution in the numerator, and this is k prime slash plus xp slash plus m naught. Okay. Did I miss this gamma mu also? The gamma mu's are there, by the way. There is this extra factor of gamma mu. So, you have combined the gamma nu with eta mu nu, and the factor of I in the propagator and the minus I in the photon propagator was also combined. Okay. So, again now this is the even function of k prime. So, you can throw away this integral, okay, k prime integration, and you will be left with something independent of k in the numerator. And finally, so let me you have to evaluate an integral of this quantity involving this quantity. Okay. So, dd k prime numerator is independent of k prime and this particular quantity. So, let me just give the result for that integral. Okay, so no, not yet. Okay, one more step that you have to still do is Not you have to do, by the way, that's what actually I want to emphasize here. Normally we do a weak rotation at this step, and because this is a Minkowski 4 vector, and k prime square is k0 prime square, and minus, let's say, mod k prime square, and in one of this integration, let's say k0 prime integration, we will encounter a pole, right, and you have a I epsilon to regulate that basically, right. So there will be, you have to calculate this, you have to do this residue calculation, right. You can actually do that, there is no problem of going through the residue calculation, but easier way you can actually use weak rotation, okay, and then make it a Euclidean integration where you do not encounter the pole anymore, okay. You can get rid of the I epsilon also. It's just basically this thing. So you have an integration like this, let's say, limit epsilon tends to 0 plus something like this, dx by x square minus a square plus I epsilon. You can do this integration using residue calculation, okay, and the result will be minus I pi by a. There is no harm in doing this, but you can use this weak rotation thing to do this also. What means actually, you choose a contour like this. So the poles are actually here and here, and you can choose a contour like this, okay, and this contour does not include any pole, okay. And because of this 1 over x square behavior, okay, if you do this closed loop integration, this part of the contour will not contribute, it will go to 0 if you take this radius tends to infinity limit, okay. Ultimately, you will be left with the integration along this line related with along this line, and it basically means this integral, if I use this contour, will look something like this, okay. It will look something like this, minus I minus infinity to plus infinity dy by y square. I can actually break down this, but I don't have the time, I think, okay. There will be I epsilon if you just make it a dz by z square minus s square plus I epsilon, okay, and z along this line is iy. So z square will be minus y square, and I have taken all those factors into account, and this integral also I took on the other side. The range will be from plus infinity to minus infinity, all these things will be there, and since there is a z square will be iy, it will be minus y square, and this is minus s square, you can take the minus sign common, and then there is no pole along the y integration, okay. So you can set this epsilon tends to 0 limit at this level, but not here because there is a pole. Without this is not well defined, but this is perfectly well defined. So the effect of all this thing is that you encounter a factor of I maybe. This minus sign is typical to this particular case, it is not important, okay. You have still a real variable integration over the real variable, okay, from minus infinity to plus infinity along variable y, which is a real variable, but somehow you have to replace this x with a minus iy, with a iy, sorry, and so the sign will change, right. So this is effectively the weak rotation, okay. You will encounter a I factor in the measure, you will encounter, you have to replace everywhere z or x by iy, but your integration limit will be still over real variable from minus infinity to plus infinity, okay. So this is what we mean by this thing. Any question on this part? So what I mean is just do this k0 prime, I will not write it equal to ik0 e. So this is a new variable I am introducing. Let us say this is, I am going into a complex k0 prime plane, okay, and this k0 prime is the real part of that complex k0 prime, and this k0 e is the imaginary part of that, okay. So you are doing along that. So I will be just saying that not equal to, it is not a substitution in the integral. You should substitute this in place of k0 prime in the integrand maybe, and also in the measure, but the limit will be still minus infinity to plus infinity, okay. So all this will be still valid. D k prime will be I times dd ke, okay. It comes from the k0 prime part, and this vector ke is k0e and k prime, okay, and k prime square since is k square. Okay. So, if you do all these things in this integral, let me write down this integral part only. You will get a you get this integral dd k prime by 2 pi to the power d 1 over k prime square minus delta plus I epsilon square. This will be equal to I times dd ke by 2 pi to the power d. So, you do not need this I epsilon anymore, okay, because there is no pole in this integral, and you get this extra factor of I, and all the integrals run over the real variable k0e, kx prime, ky prime, and so on. Okay. And there is standard result for this Euclidean integration, and that is what that was the purpose actually. Just use the standard result of this Euclidean integral, just like this tan inverse x by a thing, okay, tan inverse x by a integration. Okay. So, this result, if you separate this into angular and radial part, the result will be this. One over delta 4 minus d by 2. So, it's as long as d is not 4, this integral is a finite integral, and if you take the limit d tends to 4, you have a gamma 0, and that actually is a singular quantity, right. So, the original divergence of the integral was actually encoded in this gamma function. Okay. So, you can actually expand this gamma function near the pole, okay, d equal to 4, and separate the divergent piece and the finite piece in principle. I will just maybe without going through any further of this thing, I can just write down, maybe I do not have much time. This is the only thing I will be able to maybe finish. So, any question on this part? Okay. So, let me so use all this. So, to expand this around d equal to 4, you can just use this substitution where epsilon is a small quantity, okay, and you write down all this. All this can be derived, by the way, okay, 2 by epsilon minus gamma e plus some term of order epsilon. And you also combine all this 4 pi and all this and the delta and the mu square and all these things, you can get a combination like this. Maybe I can write down the final result without going through all these things. So, in terms of epsilon, okay. So, this is 4 pi square order epsilon contribution and then you have this 0 to 1 dx x 2 minus epsilon. This comes from this gamma mu p slash gamma mu part, p slash plus 4 minus epsilon m naught part, okay, multiplied by this. If you combine all these 4 pi delta and all these things, this will give another factor. Okay. So now you can write down this this quantity. That's if you just find out the coefficient of the term 1 over epsilon, okay, which will going to diverge in the limit epsilon tends to 0. So let me just write it down. The divergent part only. Okay, this quantity is simply just take the coefficient and then do the x integration part. This term will not contribute. Remember, this delta is function of x, so this will not contribute in the integral x integration because only the first term is important. This multiplied by this epsilon will be finite. So the only contribution that you get for the divergent piece is this quantity. Plus finite term. Okay. So this is what you get if you use Feynman gauge. In arbitrary gauge, if I have the result, I will. I think we have. Sure. Let me see. Just a second. I think I remember it. If you use the propagator in arbitrary gauge, this will come up to be something like this. There will be a additional contribution from the gauge dependent part of the photon propagator. Okay, so it will be like I squared by 8 pi square epsilon p slash minus 4 m naught plus p slash 1 minus xi times p slash minus m naught. Okay. If you put p slash equal to m naught, this contribution, this is xi dependent contribution actually goes up. You recover this one. Okay. Anyway, so this is how you calculate this, which I have already maybe you did. The thing is that how to handle these divergences, right? In the redefinition of the field and redefinition of the parameters, let's say coupling and masses. So this will maybe denormalize the mass only of the electron, and then we go on and maybe computing the other diagrams which are also divergent. Without, of course, I cannot go into that thing. So do I have time or shall I continue? Couple of minutes. Huh. Gamma? Oh, that expression? Yeah, this you have to use this expansion of this gamma function around the pole. Gamma? Oh, so value? It has a value. I don't know how from where this value comes from, but it has a specified value. Anyone has any idea how to find the value of the gamma E? No, that value I have, but I am saying any idea how to get the value of this? Go ahead.
So when you have this gamma function, then basically as he has mentioned, they set d equal to 4 minus epsilon, right? So you have a gamma of epsilon. And apart from a Taylor's expansion, the Taylor's expansion you can write down in terms of divergent term and something called the digamma function. Okay. The digamma function's value at 1 equal to gamma. This is the origin of the digamma function.
Just a second. I have two things. Anyway, have it. Okay, so if you recall, this is using this you can calculate the Z2 that we have, right, which is 1 minus d sigma dp slash. Okay, you can calculate all these quantities. Forget this extra piece, okay, and this will comes out to be, I think, 1 plus 8, 1 plus e squared by only the divergent piece of Z2, let's say, there will be finite piece in it, okay, 8 pi square epsilon plus yeah, the finite piece will be in the and you can also using this relation you can also see how this physical mass near p slash equal to m. Using this relation, okay, you can also calculate what is m, how m is modified in with respect to this m naught in the with respect to the Bayer parameter. I think you will get something like this: 1 plus 3 square by 8 pi square epsilon times m naught. So you see, the physical mass will be infinity if you take the limit epsilon tends to 0, okay, unless you say that this m naught is not a fixed finite parameter, right, in the Bayer theory. Okay. If you think of this m naught is a fixed finite parameter, it has a fixed value, okay, finite value, then the physical mass will be divergent. Okay. This only maybe makes sense if all these are yeah, anyway, can you hear me from the back? Yeah. So, if you treat this as a kind of unphysical parameter, if you take this to be maybe infinity, so that this combination is finite, this has to be your physical mass of the electron, right? So, you treat this whole combination or treat this m naught in such a way that this product is found. Okay. This is one way of your interpreting that you are actually normalizing the Bayer parameter of the theory, but the another way of this, because if you do a parametric calculation using the Lagrangian that I wrote, which has this Bayer parameter and Bayer coupling, and which are not fixed, which doesn't have any fixed value, there is doesn't make any sense to do calculation in terms of those parameters, right? So better you write down a Lagrangian which has some fixed finite parameters, maybe the physical mass and the physical coupling. And you can actually, so the method of bookkeeping will be this. So you rewrite the Lagrangian that we had earlier, but in terms of physical masses, let's say, or maybe renormalized masses and renormalized coupling, but adds additional counter term into the Lagrangian, so that you cancel the divergences that you encounter. So yeah, so recall this. So I'm just illustrating this with only one example, but there are other divergences that you need to calculate in this theory, which is the 3-point correlation function, the Vertex function, and also the photon propagator. And so this was our starting point. Not only this fields are Bayer fields, the couplings are Bayer coupling, and this doesn't make any sense in this way. So the 2-point correlation function that we calculated in terms of this field has this behavior already, right? We have seen this, right? This in the momentum space, the 2-point correlation function at one loop near the pole, it was something like this, Iz 2 by p slash minus. And this is already a divergent quantity. Okay. So instead of using psi, if you use this renormalized psi, let's say z2 to the power minus half psi half, and calculate the 2-point correlation function using this renormalized field, you can get rid of this z2 in the Anyway, I don't think how far I can continue.
Yeah, I think sometimes you have to finish in next couple of minutes.
Okay. Anyway, I just promised you that I will be finishing in the middle of November. So, yeah, just finally I have to go through this all this. I have to split this Lagrangian into in terms of, let's say, renormalized field and renormalized parameter and the counter term. Okay. So, yeah. Let me write down this, maybe at least this much and then stop. So, you renormalize at all the fields that are there. Okay. So, this is in terms of so you have this Lagrangian in terms of so what I just did, I just replaced all the fields, let's say, with this, okay, and I have this extra term minus 1/4. This labeling that I am using is conventional labeling that people uses. And plus psi bar r delta 2 del slash minus delta m. I have not added all the counter term yet. What I did just is this. I just renormalized the field psi, and let's say if I calculate the photon propagator, I will encounter the similar divergences, okay, and it will have, let's say, this I z3 by q square kind of behavior, and you renormalize only the field and this, and you will replace this m naught. You split it into physical mass plus some extra delta m contribution, and you will encounter actually this, okay. What it actually gives you, this is not yet the full fixed Lagrangian that will give you finite result, okay. Even with this Lagrangian, if you calculate the 3-point correlation function with this coupling that I have here, I will encounter further divergences, okay. The 2-point correlation function that I will calculate will be finite. For that, I have to fix this extra contribution that I wrote down here. Let me give you these relations, and then maybe I will stop. This delta 3 will come from the renormalization of the photon field, okay. The delta 2 is Z2 minus 1, and delta m is Z2 m naught minus m. So, if you put this z here, Z2 here, you will get a multiplication factor Z2 here, and then you write it down as a physical mass plus extra piece, okay. So, even with this theory is not finite. At the 3-point correlation function that you will be calculating, you will encounter a divergence again, okay. So, somehow you have to then renormalize this particular parameter E0 that you have here, which is already multiplied by these two renormalizations factor, but there will be additional factor which is historically called Z1, okay. And once you do that and add the counter term for the 3-point correlation function as well, okay, then at one loop you renormalize the quantum electrodynamics by suitably adjusting this coefficient that I added here, okay. Maybe I can only stop at that level if you have any further question.
Questions?
Everybody knows this topic anyway.
If not, then let's try further once more.
I apologize. The organizer gave me a very late notice and said that you have to discuss normalization with the standard model.
Wait.
Oh, yeah. Now it's okay.
Okay, now it's okay.
Okay. Okay, so we close the session today, and tomorrow we are meeting at 10.
10:00.
10:00, not 10:01. So we started at 10:00. Tomorrow we are going to start at 10:00.